the YouTube site.
All right, good morning, everybody. I hope you can all hear me well at this early morning. It's my pleasure to welcome you all to the Rhino workshop Beyond Rigid Worlds Representing and Interacting with Non-Rigid Objects. I think this is also the first event at CoRL this year for everybody, and also warmly welcome you all to this year's conference. Hopefully it's going to be a really cool experience, a lot of nice exchanges, and a lot of good inspiration. So this workshop is about the challenges and emerging approaches for robotic perception and manipulation of non-rigid objects. I think there has been a bunch of recent publications which just exemplify the need for this, such as some examples from our sponsor, Lightwheel, and several publications at previous CoRL. We have a really cool all-star team of organizers. The highlighted people here are also present at this year. Maybe you can just wave your hand shortly. There's Holly in the back managing the live stream. There's me, Marcel. There's Alberta over there. assisting with the panel later on, and Mingri, not sure where he is right now, probably organizing something. Why are we doing this workshop? Because non-rigid objects are everywhere and they are hard. So one example is making the bed sheets, which to make that in a nice way is already hard for a normal human being. And then we have a bunch of highly deformable objects in everyday, like taking out the trash, working with dough, or also tying shoelaces, which takes a while for small children to learn. And the problem is we have highly dimensional configuration spaces, and the state representation there is extremely complicated. So this means that there is a lot of topics actually going into this field of research. I'm not going to go over each and every one of them, but it's a mixture of perception problems. You can usually overcome some complications by including approaches from simulation and generative models, rely on active sensing, and of course, several methods to increase robustness of this. For everybody joining in over the live stream, we have some Slido set up where you can scan this QR code and enter the code, where you can ask our questions, and Holly will pick them up if there's time and ask them here in person. I'm going to keep the QR code while quickly going over our schedule. So first we're going to start with some academic perspective from our speakers, and then we're going to have our spotlight session where the speakers from our spotlights are going to present their posters, which are then you have some time to actually talk to them in person during the coffee break. And then we have three more invited speakers, Yunsu Lee from Colombia, Steve He from our sponsor Lightwheel, Zhuang from the Beijing AI Institute. And afterwards, all of them will come back together for the panel discussion, and then we will all go to lunch together. So it's my pleasure to invite our first invited speaker to the stage, Janet Borg, who is an assistant professor for computer science at Stanford University. She was the group leader at the Autonomous Motion Department at the Max Planck Institute in Tübingen, and she received her PhD from the KTH Royal Institute of Technology in Stockholm, which is a special pleasure for me because that's also where I'm from. So yes, Janet, the stage is yours. So that's fun.
Oh, right. Okay. Hello, everyone. Hi. Thank you for the introduction and also for the invitation. I did change my title slightly. I think my first title that I thought about like many months ago was like a little too catch-all. Today I thought I'm going to talk a little bit about basically that there is not a universal representation for the formal roles. And I want to discuss this a little bit with you maybe during my talk or during the Q&A, but then also maybe this is a topic we can also talk about during the panel as well. So I want to start or set up this discussion a little bit. And so for this, I just want to show you a few examples from the work that we have done in my lab with the formables. And you see it's a diversity of tasks, all sorts of different tasks, because of course in robotics we always pick the task that works best for our particular paper. That is like another problem that we could discuss at length. So one thing I want to emphasize here is that in these works, we are using completely different representations for the formables. So for example, on this particular work, everything are RGB images, while in this work that is Equibot, we use SAM for segmenting objects and the point cloud representation. Here in this work called TidyBot, we used top-down image of the scene and then segmented all the different objects in a very simple way. In this work, we used an RGB image, and in this one, again, this is like a predecessor of Equibot. Actually, we use SAM and point clouds as well to do this. So, all of this emphasizes that even in my lab, just in my lab, there's no one representation that we're using for all of these different tasks. And today I just want to contrast two very recent works that we've done, which emphasize or kind of highlight these differences. So the first one I want to talk about today is called, let me see, is this actually video? Yes. So this one is called Masquerade, which we just uploaded on archive, basically. It's in submission, and there we learned a representation for all sorts of tasks that people might be doing in the kitchen. And we are only using RGB images there. And that is, I would call, a non-object-centric way to represent the formables. And then, so I'm going to talk about this one in more detail next. But the second work I'm going to talk about, the second part of the talk, is a work that is more object-centric. So we're assuming we have a segmentation of the object we care about, of a deformable object, and we're going to use point clouds to represent it. And we found that including topological and geometric information to represent point clouds actually helps us to do very difficult semantic segmentation tasks or semantic understanding tasks with these deformables, which might also help manipulation downstream. So let's talk about this first work called Masquerade, where we learn basically a representation of deformables from in the wild human videos using a data editing technique. And so why would we learn from human videos? Well, first of all, of course, human videos are way more abundant than robot data sets out there. So here I'm showing two egocentric video data sets, Ego4D and Epic Kitchens. And even if you just look at curated data sets for this data, they are already way bigger than what we have, for example, the OpenX embodiment data set that only contains robot data. And then, of course, it's way easier to scale up data collection with for human videos, because there are all these phones out there that we have in the back of our pockets, so we can just use them instead of using specialized devices like either an entire robot that we are lugging around or universal manipulation interfaces, these portable data collection methods, for example. Okay, but of course, learning from human videos is really hard for a variety of reasons. So first of all, there's a huge embodiment gap between humans and robots. And the embodiment gap is actually twofold. The first one is visual. Of course, the human hand looks very different from a robot hand. And that's hard for vision-based policies, for example, to somehow get around. And then videos also don't contain an action label directly, right? So there's no joint information, no hand pose natively kind of provided with them. You actually somehow have to extract this from the video. We need to know where in 3D space these human hands actually are. And only then we can somehow match the robot hand to them. And then there is a large physical embodiment gap. Can't actually follow exactly the motion that humans are doing. They are literally physically impossible for humans to do. Some of these things that you see here in this video, the robot couldn't do because maybe it has just 2 fingers or 3 fingers. Maybe it doesn't have a cool wrist. Turns out our wrist is actually extremely important and makes some of these actions that we see in these very complex egocentric videos feasible at all. So that's another challenge. And then, of course, there's no force sensing in these videos, right? Like, which for subtasks might actually be necessary to get them done. Okay, so these are all the challenges that I see in learning from human videos. And in this work, Masquerade, we actually going to address the first 2 of them. So we're going to bridge the visual embodiment gap, and we're going to provide action labels. Okay, so why is it hard to learn from in the wild videos? There's also the way, you could also think of a different way. You can just like collect your own human videos that are more favorable to learning with robots. But we really wanted to unlock the scale from in the wild videos. Like, for example, in this Epic Kitchens data set. Well, actually, this is a video from Kenji Lopez-Alt, but you get the idea. So the problem is that in the wild data has no depth data. While kind of curated data that you collect in your own lab, you could actually use a depth camera, but these data sets don't have that. They're really heavy occlusions as well of the fingers, and arms go out of arms and hands go out of the frame as well. There's lots of camera motions here, so if you watch this video actually on YouTube on full screen, you might get a little bit sick too, because his head-mounted camera is of course moving around. And then what is really cool about these videos, but also makes it really hard, is that they have all these dexterous graphs, right, like for using all these tools. This is why it's really challenging to learn from these videos instead of learning from kind of curated videos that you maybe collect in your own lab. So in order to address these challenges, what we do is we implement a bunch of filtering filters to basically filter out frames where the robot isn't accurately tracking the motion of the hand, or we filter out frames that have an extreme amount of camera data. And ideally in future work, we could relax this filtering. But even if we filter out this data, we still end up with an order of magnitude more robot data than what we actually have. Or we end up with an order of magnitude more data than what we have in robotic data. Okay, so that leaves us with addressing this problem, that there is no depth in these videos. And why is this a problem? Well, depth data was critical in one of our prior works, so we also learned from human videos, but from hand-collected one, not from in the wild videos. And we needed it to get accurate hand-use information from this video. And it was also critical to get overlays between the object that is manipulated and the hand actually correct. So with depth, when you render an image, you can easily tell which pixels of the robot should be behind or in front of the objects, but without depth, that's really hard to know. And so you end up with overlays that look more like these ones here on the right, which sometimes don't really look realistic. Because of this, of course, we tried many things, actually, like monocular depth estimation methods, which turn out to be not as good yet as one might believe from the papers that are out there, especially at vision conferences. So we basically found these challenges, and we therefore proposed a particular model that is not yet directly learning a policy from these videos for a robot, but uses instead these videos for visual representation learning. So what we do is we take this data set called Epic Kitchens. So it's basically normal people wearing head-mounted cameras, and they do completely unscripted tasks in their kitchen. So there's no instructions on what to really do. And this is kind of how they look like. And then our approach is actually adopted from a work called Phantom, which we present here at CoRL later this week, I think on Friday, on the 30th. It's not Friday, it's probably Thursday. Sorry, I'm like a little, I kind of am losing time and date ideas. Anyway, so this approach, the way it works is we basically take an RGB image, one of the frames in this video. Then we use a method called Hammer for hand tracking to extract basically the human hand pose, so the wrist poses, and also the finger configurations. This method works better than anything that was out there prior to this method, but it still has a lot of noise. But it's good enough to get these actions most of the time. And then what we do is we use an in-painting method to actually basically delete the hand and the arm of the robot from the frame. And you see here in this in-painted video that this actually looks very realistic. So we were actually surprised that that works so well. And then we overlay a virtual robot. So we basically have a way to do retargeting between the human hand that we detected with Hammer and the robot whippers. And then we basically solve for inverse kinematics and paint in this robot. And so this is kind of how this looks like side by side, where you have the video that shows the person, and then you have the edited video where the robot is in. And I just want to, I picked, or my student also picked this video specifically because it has deformable. So I don't know if these are zucchini or onions or whatever, but this would be really hard to physically simulate, for example. Here's another cool one where a person actually makes some tacos. That also looks really cool when done with a robot. But you can also see that some of these overlay problems here as well, that I talked about before. So I can play this again just to show you. Yeah, but this is extremely diverse data, more data than we have available for robots, and with objects that are really hard to simulate as well. And so here's a collection of these edited videos and how they look like. And you also see the diversity of the backgrounds as well, in all of these different departments from all of these people. Okay, so I already told you, so now we have this data, we edited it, and it looks kind of like fake robot videos now, as if we had teleoperated a robot. But I also mentioned that we have no depth in these videos, right? And so because that means we have a relatively inaccurate 3D position of where the robot now actually is, we couldn't directly learn a policy from this. I think this is something we want to do in future work. But for now, what we did is we learned a representation. And so the way we do this is and by the way, we also, of course, compare to existing vision representations like ImageNet and all of this. Yes?
Sorry, can I ask a quick question? How do
Yes.
you overlay the virtual robot hand? How do you solve for the poses of the hand?
Yeah, so we have to kind of calibrate the camera. So we know exactly, let me actually show you a slide that I had removed, but yeah, this is definitely something that is confusing. So let me show you this slide. Okay, this one. So here you see basically Marion, the student who is the first author of this paper, kind of overlaid with the robot, how it would look like. So this is the robot that we use to actually then do the policies. And we have exactly the hand-eye calibration, right? Like, so we know where the camera is relative to the hands. And so now Marion or any of these Epic Kitchen people who collected data in there, we basically assume that they have the same hand-eye calibration, right? So we see their hands, and once we see the hands, we kind of know, like, okay, that means the camera must be roughly here, right then. And that's how we do the imprinting. Does that answer your question? Okay. More questions on this? Okay. Let me move that. Okay, so as an auxiliary loss, basically, so that you see visualized kind of here on the right side. So basically what we recognize is that we don't have accurate 3D, but what we get from these videos really accurate or fairly accurate 2D pixel location of where the robot needs to move. And so we use this as a loss for this data set. And we also, using a homography projection racing, we take the future movements of the object and project it back into this initial frame. And so these trajectories we basically use as the training limits, essentially, to train this vision transformer, which, by the way, that one is pre-trained on ImageNet as well. Okay, so now we have a visual representation, and so now how do we get to the policy? Basically what we do is we take about 50 robot demos for these different tasks that I'm going to show you in a bit, that were collected in a single scene, and during training these demos are passed through the same vision encoder as the human data, or the fake robot demo data if you want, as well as so the action policy. And then the action policy is just trained with the normal behavior cloning loss. We use diffusion policy in this case. And so one important point that we had to do was actually co-training. So while we're training the action policy, we also keep basically co-training with some of these fake robot videos that we created with this auxiliary 2D loss. And so here are just some visual results of how this looks like. So here are some tasks that are fairly long horizon, like stacking these pots, for example. And you see on the very left, you see basically the way or how the scene looked like when the demonstrations were collected. And then on the right, you see all these out of distribution scenarios where Marion just threw in a bunch of things into this. Here's another task that is just like scraping potatoes into this pan, or sweeping some chilies off, this surface. Okay, so I show you just some results. So here are the baseline. So we basically use some very commonly used vision encoders. that are used in related work a lot. So ImageNet and DynoV2. Interesting to also try DynoV3 at some point. And then we use this particular baseline that had the same auxiliary loss, but doesn't use this data editing. So these fake robot videos that we use uses 10 times more egocentric human videos, but no co-training. And then we have our approach. And so basically this is how the picture looks like, right? Like, and one note I want to make is like, this is specifically for out of distribution scenarios. So if you go out of distribution, then pre-training with these fake robot videos gives you a lot of advantage to basically generalize over these new scenes as well. Here's some data on how this looks like if you don't co-train or you don't overlay. So there's a huge drop again in performance. And then just to convince you that we did the correct implementation of all of these baselines that we had, here's the data of how things look like actually in distribution, right? Like, but you have this huge drop in out of distribution scenarios. And here's another cool plot that we did. So if you actually increase the number of data or frames that you have in this from humans, the performance and success rate of these policies actually goes up, and you see it's not yet plateauing at all. So even adding more data from human egocentric videos looks like it could really help, especially in these out of distribution scenes. Okay, so here's just like a summary of these of this work again. So we co-trained with individual human videos, and we really showed that this enables scene generalization for these tasks. This data editing and co-training was really important. And what we're going to do next is actually to try to train a policy directly on this data. So let's see how this is going. I also want to remind you, we used a very particular robot, but you can paint in any robot that you personally have at home or in your lab. Okay, so so this was a work where we decided to use a non-object-centric approach and also only RGB images because that leverages all the knowledge we have for policies that are using RGB images only, right? Like there's a lot out there, but there's much less policy architectures that are actually using 3D data. And also, we unlock these video data by using this. But of course, we have all this issue with depth. And so what we also, in my lab, we also look at different ways to represent performables, for example, using point clouds. And so here's one of our most recent works that isn't even yet on arXiv that I wanted to, at this point, briefly talk about. I have 6 minutes left. And so I think that for tasks where you need a more semantic understanding about deformables, it might actually be useful to have depth data. And specifically in this work, we are using topology and geometry together to get a better semantic understanding of, in this case, these clothes that I showed here. So here's some tasks that we think would really benefit from semantic information. So for example, hanging tote bags or just putting your groceries into a tote bag, or maybe take them out when you come back from grocery shopping, or dressing people as well, or just hanging clothes on hangers, for example. I also want to note that all of these kinds of objects, they have topological features like holes, for example. And to me, these kinds of features, they are probably easier to capture if you have depth information that provide geometry, which is different from RGB images. And so in this work, we combine topology and geometry and to deal or to represent deformable point clouds. And so there's not really a lot of representations out there for representing point clouds that are actually deformable. Most of the work out there has actually been developed and then evaluated on data sets that actually only have rigid objects, maybe articulated objects as well. And so these include architectures like PointNet, PointNet++, DGCNN, and so on. And these methods that are geometric deep learning methods. They exploit local geometric structure with simple methods like k-nans or ball queries in a local area. But the question is like, is this all we can do, these purely geometric methods for deformable objects? Or is that all we need for deformable objects that actually undergo continuous non-rigid transformations that disrupt these Euclidean relationships, right? So here is a tote bag, for example, a common deformable object that we all kind of have at home, probably too many of them. And let's say this robot wants to place objects into a tote, right? And so we see in pictures like with this one that the semantic part segmentation is quite straightforward, right? Like you find maybe first the body of the bag, which would help the robot to know where to grasp, right? Like, and here are the handles, super easy. Super easy, like probably pretty easy even with RGB methods, right? So that's fine. And then this is also where this ball query that all of these other works for geometric point cloud processing actually use, right? Like, because there's not a lot of overlap between the point cloud from the handle versus from the back. But now let's look at other common configurations that such a tote bag is actually undergoing. So here's some tote bags in the real world, right? Like where if you wanted to do semantic part segmentation and figure out where the body of the tote bag is and the handle, then you see that suddenly these things are actually overlapping and even touching each other. And this is when this ball query that is used in these other works actually doesn't work quite as well anymore, right? Like it contains basically parts from both semantic parts here, exactly. So what we propose in this work is to do topological data analysis to capture the connectivity structure that remains invariant even under continuous deformations that these formables are actually undergoing. And the problem, of course, is that there are no benchmarks for this. These are all benchmarks, really commonly used ones that are out there, but of course they have most articulated objects, so consist of one or n parts. So we came up with a new data set to just evaluate our method and compare it to other point cloud representations, and we call this Fabric DeformNet 3D. It has like almost 40,000 annotated point clouds of these 15 different classes with 65 different semantic part labels. And also they have, each class has unique instances for each class, like for example shown here for bags, dresses, and skirts. And we also make them move. So here's just some different types of trajectories for different object classes. We inject random noise also and vary the camera viewpoints to have diversity in its trajectories, but also represent in the point cloud self-occlusions and things like that that are, of course, common in these deformables. Okay, so this is our data set that we will make open source very soon with, as you can see, all these semantic part labels, which, by the way, are also really hard to come by. But I'm not going to talk about this today, how we got there. And instead, let me just briefly talk about the model that we actually proposed. So this is basically a network we call TOMNet, Topometric Graph Neural Network. And it aims to fuse topological and geometric representations to improve semantic part segmentation on formables. And basically, since I'm out of time, I'm going to make this really fast, so you're not going to understand anything. Sorry for that. But basically, we use the mapper algorithm, which is a really common tool for topological data analysis. And I have this awesome explanation that I'm not going to go through for this mapper algorithm, that you just need to know that it basically creates a graph in which topological neighborhoods are basically really well connected within each other, and then there are connections between different topological parts. And we do this for 3D, really great. And then we also connect everything over time and temporally as well. And then we have like a very complicated network architecture that I'm not going to explain, and really great results. Really cool. So I just want to tell you I'm just going to show you some qualitative results compared to our strongest baseline, which is DGCNN, which is actually fairly old, but it turned out to work the best. So here are some results. And you see that actually all of these methods, they're working pretty well on like uniform neighborhoods, but where things really matter is at the seams basically of these parts. So that's where our method does better. And here are some, of course we do this over time and all of this, so here are some cool animations that I jump over. So I talked today about these two different ways to represent deformables, really different ideas, really different inputs. And I don't know how to bring these together. Both have their pros and cons, of course, and I'd love to discuss about this like maybe later during the panel discussion. So thank you very much. Here's my great, fabulous research group, and thank you to all the sponsors.
Test, yes. Thank you so much for the audio. Also, thank you, Jeanette, for this amazing talk at this early hours in the morning. And also, thanks again for everybody who showed up now. We are already out of time, but since this is a workshop, it would be a shame to not spend a few more minutes for some questions. I think we can allocate 5 more minutes. And there is a microphone over there in the middle, so feel free to come forward to ask your question there. So also the live stream can pick it up.
Hi.
Hi, nice talk. So now that you've gone to the trouble of building those graphs, have you considered putting them into a real physics engine like Mujoko, for example, which has these flexible bodies ready to simulate, and they would run like orders of magnitude faster than your network?
Yeah.
You're basically getting the data that you need to build a Mujoko model. You're going to do a little bit of system ID to tune a bunch of softness parameters to get the cloth to behave the right way, but you can do that. And then you can do all kinds of learning on top of it.
Okay, yeah. Use Python actually, and a framework called Dido for deformable object manipulation. But Python, of course, is not dead, but
Yeah.
it's not maintained anymore. So yeah, that's a great idea, but we haven't considered it. More questions?
Maybe I can ask one. I actually have two. I will start with the first one. You discussed
These terms that are super well defined in our community, you know, like tasks or what an object actually is and all of this. But yeah, so basically the way we defined it in this paper is that we basically put a lot of basically different surfaces and different objects into the scene so that it visually looks extremely different. Well, extremely different. Looks pretty different from the scene that we actually collected information in. Yeah. So we didn't go necessarily to different kitchens, which is mostly because we ran out of time. But like as it always is. But yeah, that was our first attempt at doing out of distribution.
okay, thank
Yeah, but you see it, like I want to say, like this is visually out of distribution, right? Like the scene, the actual task relevant objects. I think they also move around a little bit, but that is in distribution, right? Like so one of the things that we see is like actually with all these VLAs that are around, they because they have a VLM inside of them, right? Like they actually generalize pretty well to different language, different visuals, and all of this, maybe even different objects within the same category. But because we have so little data in terms of the actions, actually, they don't generalize well to different actions. So for example, having this task done maybe in a different order to stack the tasks, the pots, for example, that wouldn't work, right? Because it didn't see the data for this. Anyway, this is a single task diffusion policy and not a VLA. But yeah, it's basically seen out of distribution here.
Thank you.
Okay, thank you. Thank you for the great talk. I have a more philosophical question, perhaps related to the panel. So this is a really great pitch of like object-centric or not. And I really like the first talk because it's just so much more scalable. And so I myself have been working on deformable objects for a long time. But then I actually think these are the categories in which actually video models do much better than the simulators or any of our deformable representations. So in that sense, the first work is really scalable, right? So then I think that is the question. It's like, should we really work on doing something on the latter of that part, and then like how much do you think this helps and stuff like that? Thanks.
Yeah, this is exactly the kind of question I don't exactly have an answer for and just hypothesis. So yeah, let me just bring up this slide, right? Like where I contrast these two. Yeah, so for sure, if we can use these videos, we get scale. I wonder though, we get scale visually, but potentially, which we haven't done yet in this work, also in terms of the actions that can be done, like even using tools and all of this. That's really cool. So that's very promising. And again, these are very hard to simulate objects, right? Maybe, perhaps, if you get depth, you can be more precise. I don't think there's evidence for that yet, actually. I think intuitively, as a community, we probably, a lot of us believe that if you feed a policy like this with depth data, you would actually get more accuracy. Certainly, because we don't have depth data, that's why we couldn't get trained policy directly on this, right? So that's one. And the other one is maybe if you have depth, depth also has a smaller sim-to-real gap as well, but not for simulating deformables necessarily, right? But just depth as a perception modality has a smaller sim-to-real gap. So potentially you could scale up there if you make the simulation more realistic, potentially, right? And then if these things are true, then you can probably understand these objects more in a fine-grained manner as well. Like, for example, where exactly the theme is. And that means you wouldn't need to collect data on a physical robot for that either, but you could do it in simulation. But yeah, so I think right now I'm also really excited to learn from human videos. But I think depth has promise, but there are lots of open questions there, like what is actually the right encoder to train a diffusion policy, for example, or a VLA with depth. Right now, we don't know. Actually, the performance drops when we feed in depth, usually in the diffusion policy, which is very puzzling. And then again, simulation for these methods is not good yet. Yeah.
I think we're out of time for questions, but feel free to reach out via mail.
Thanks.
Or there is a panel later on, in case you want to ask questions to all speakers. So short round of applause for Jeanette again. There we go. Yes, now it's time for our spotlight presentations. So there are going to be posters later on during coffee break. But for now, we're going to show the short introductions for those posters. Each of this is about 3 minutes long, and then we have 1 minute allocated afterwards for 1 or 2 short questions. Please keep it short. One specialty is that the presenter is supposed to air dirty laundry to increase capacity and like transparency in the community. So don't wonder when these short presentations spend a long time talking about the limitations and what's not working yet. So you see what's going to happen in future work. When you see your presentation playing here, please come forward. There are some chairs there to be ready to accept the questions, and maybe you just come up here to the microphone to answer them. Yes, and on the right side you see the list of papers, and we're going to play the videos one after the other. Sorry, I need to connect the audience. Cannot secure it.
We present a unified framework composing strongly coupled multi-physics for robotics simulation. Various robotics problems involve complex interactions with non-rigid objects. One of these is bio-inspired aquatic locomotion. While studied heavily by the hydrodynamics and biology community, such a phenomenon is yet to be realized on a robotic system, which we attribute to the difficulty of modeling the complex physics involved in the fluid robotic interaction. Therefore, we present a unified approach intuitively posing and modeling non-rigid body interactions with robots. Specifically, we formulate the combined detection principle to model the multi-physics as a single continuous time optimization problem. Using calculus of variations, we can derive the incompressible Navier-Stokes and manipulator equations, which are coupled together by constraint force that enforces the no-slip condition. While other simulators utilize these individual equations with obscure coupling forces, we leverage variational mechanics to discretize the optimization problem directly, resulting in simulation of the full multi-body robot jointly with the surrounding fluid. We then validate our unified approach by simulating a squid-like swimming robot before realizing the experiment in real-world hardware. As shown, our approach is aimed to simulate the resulting forward movement seen on open-loop hardware robots. Meanwhile, a baseline multi-physics simulator is unable to properly model the fluid-robot interaction under similar fidelity. We attribute this to the particle-based representation of the fluid, which is tailored towards other robotics tasks such as manipulation. While theoretically promising, this unified multi-physics framework still has dirty laundry to aim. One of these is the need to sit down and formulate the action for each physics. As with other forms of implicit integration, the resulting simulation can be computationally expensive to compute, with additional efforts needed to work with other various compute architectures like GPUs. Finally, the coupled Navier-Stokes robot physics can be difficult to scale to 3D due to computational constraints, restricting the types of aquatic locomotion problems that can be simulated.
Yes, thank you so much. I think we have the author over there, so please come forward.
Any question from those? Yeah, thank you. Oh, yes, no, go ahead. Hello.
Hi. So I think your paper is really interesting. One of the questions that I had sort of reviewing it is like so we see like the one swimming task, like the straight trajectory. So I'm glad you mentioned the scalability of fluid dynamics to 3D because that was actually going to be my first question. Second question is, does adding rotational motion also impact?
Yeah, I can answer both questions. So first one is like, yeah, so scaling numbers over 3D is like phenomenally a really difficult task. So all simulation that you see out there in 3D usually rely on either compute clusters or reduced order models, or usually implement, they have to sacrifice physical accuracy, essentially the way they model the fluids. Just because Navier-Stokes really still just insanely difficult to simulate. In terms of adding 3D components, yeah, so we had time to have one benchmark of the forward swimming. That's 3D rotations. Actually, there are essentially some limitations in terms of how you model your constraint in the optimization problem. So a lot of methods from the CFD community, the way they model constraint, actually you can get physical artifacts that where adding rotational movements we actually see on our end some kind of less like some sensorial gaps in there. And right now that's something we're working to address is by having coming with new ways to formulate constraint that that the CFD community traditionally hasn't actually looked at.
Just to maybe follow on that. I think when I kind of read your paper and saw your video, I thought I was thinking about downwash in like helicopters and how downwash is an extra force that acts on the body of the.
Right.
So would that be something that you could also incorporate here?
Yeah, for sure. And for the downwards the helicopter problem, these are all the full 3D settings. So the same like scalability 3D settings can come into play. But theoretically, yeah, this is like I would say this is how you would theoretically accept the problem. So I think here we focus more on this theory in terms of like how do we think about multi-physics from theoretically from ground up in a different way where you can model the kind of the error terms that from the traditional simulators for the applications can apply.
All right, thank you so much. All future questions, ask you to direct when he's presenting his poster. Short round of applause for this, really amazing.
In this work, we present the novel framework to train real-world robotic agents for object state change manipulation task. The dominant paradigm in robotic manipulation today heavily focuses on rigid body kinematics, involving tasks such as pick and place, open and close, and so on. However, a wide range of real-world human manipulation involves object state changes, such as matching, spreading, slicing, when an object's physical and visual state evolve progressively over space and time, often in an irreversible way. Hand work in OSC manipulation often focus heavily on the task's mechanical aspects, rely on simulation, or require teleoperated robot demonstrations. Importantly, these efforts lack general purpose vision feedback, tackling each task in isolation. In this work, we present Sparta, a unified framework that offers a vision-driven solution applied across the broad family of object speed change manipulation tasks. To do this, Sparta leverages spatially progressing object change importance, or SPOC in short, which segments an object into actionable and transformed regions as the interaction unfolds, providing pixel level detail of spatial temporal activity. Our key insight is to leverage these SPOC maps as an abstract and general purpose visual representation to drive intelligent robot behavior. Sparta leverages SPOC simultaneously as structured policy observations as well as dense rewards to capture incremental transformation over time. This representation enables two policy variants, a sample-efficient RL policy for fine precision control and a greedy policy for fast deployment with no training overhead. We test Sparta on 3 different OSC tasks across 10 diverse real-world deformable objects. Sparta decisively beats baselines. We trained RL policies surpassing greedy control in complex fine precision tasks. Here we show the training process for Sparta's RL policy variant on the red copying task. We find that in just 3.5 hours of real-world training from scratch, Sparta is able to learn to code around 60% of the bread, even learning effective strategies such as reversing on object boundaries. We compare against binary success reward and state-of-the-art bone-conditioned dense reward baselines. While binary success is too sparse for effective learning, even the dense goal-conditioned method struggles on its fine-grained progress task, reducing to sparse-like behavior due to lack of stable rewards. Here are zero-shot results for spreading ranch on chase. We find that Sparta is able to transfer its learned policy to visually distinct objects while the baseline struggle. Sparta also shows strong performance in the Martian task using a broad-based measure, while also excelling in using nano tools like a cutting knife, which requires greater localized precision. Failure cases arise when the mechanical aspect of the OSC task might require human intervention to stabilize the object, or cases where object geometries are widely different from the training data. For more information, please visit our project website.
All right, thanks so much. We have one more here.
Hi there. I probably missed this in the talk, but in the beginning, Priyanka said something about it's a unified model for all of these different tasks. So the actual policy that the robot is executing, is that something you control by language, or is it just visually determined what the object is and then it switches to this action, or how does that work?
So by unified, I think what Priyanka is talking about is like you have a unified visual representation for all these different tasks, right? So you can all create a mask where like either the object is transformed or it's not transformed, right? And then you can generate the same reward function for all these different tasks using it.
And then how are the actions done again?
Right. For different tasks, we actually have different action space. So like for example, for the coding task, our action is like moving in the 2D space, and then for the cutting, it has the additional like go down. Right.
And then how many pieces of toast did you use during it? Sorry.
Like somewhere between 50 and 100.
Thanks so much.
Hi, my name's Nikhil. I'm at UC San Diego. And today I'm presenting our work, Chicken.
Sorry, I was playing twice, but on the wrong screen.
Hi, my name is Nick UC San Diego, student at UC San Diego, and today I'm presenting our word jiggle. Presenting our word jiggle. Consider the problem presented by these two deformable tissues. Now, just by looking at them, can you tell me where they're attached to the environment? No, right? To do this, you need to actively interact with the environments. And the natural next question is, well, what action should you take next to recover more? These are the questions surgeons think about all the time. They constantly manipulate tissues in the environment to understand the structure and attachments. This is that a large part of operations are spent either removing or creating these attachments. Inspired by this, we present Jiggle. Our method uses the discrepancy between simulated and observed interaction to compute a probabilistic update on boundary attachments and inform safe future actions. Our method is divided into two parts. We're going to start by talking about estimation. Our method leverages a fully differentiable PBD simulator. We model our boundary attachments as springs of varying strengths that attach the tissue to virtual particles that are fixed in the environment. We use an extended Kalman filter to probabilistically track these boundary attachment parameters. The key component of computing these updates involves computing the Jacobian matrix, J, which we efficiently compute by leveraging our differentiable PBD simulation. We demonstrate our estimation method on real-world experiments. We suture chicken skin onto pieces of chicken thigh to create attachments. Notice the uncertainty decreases in the deformed regions shown in blue, while the estimated attachment points shown in purple begin to closely match the sutured region. Now we move on to active sensing. Our active sensing algorithm aims to maximize information gain by deforming uncertain areas of the tissue while respecting safety critical constraints in surgery. To select the next action, we iteratively refine large action samples using gradient updates before selecting the best sample and taking a step in its direction. Here we show some results in simulation on active sensing. The video shows regions of increased confidence in blue, and the graphs show entropy reduction and boundary energy. Notice how our method takes actions to intelligently decrease the entropy while keeping the boundary energy below a certain level. The estimated shape uncovered by our active sensing strategy matches the partial ground truth. Our approach also supports topological changes in the boundary conditions such as cutting. We incorporate priors on topological changes into the Kalman filter's motion model. Here we show an example where we use our method to iteratively estimate and cut attached regions of the tissue. Despite its success, our method is still limited to thin shell tissues due to perception challenges like volumetric occlusion and unobservable internal.
Where the attachments are, but
Yeah, so in terms of the accuracy that I think generally it depends on how you set your stiffness parameters and stuff like that.
so you have to do system ID on that.
Yeah, so this builds on kind of a previous work, which has kind of this online adaptive stiffness parameter setting, and that allows us to kind of match the real distance gap a little bit better.
Hello, yeah. I was wondering, in the real world, especially when you do the estimation, I guess that your Kalman filter is based on state information. How do you get the state information in the real world?
Yeah, so the state information is using kind of we have a stereo camera, and then we do point cloud estimation based on that, and then we register the point cloud to the tissue. Yeah. So
Which I guess works with because you don't have too much deformation every time step, right?
yeah, so if I think this would also suffer if there's like very large deformations, like you were swinging around a bat or something like that. I don't think this would succeed, but in surgery, usually things are pretty quasi-static and slow, so it works pretty well for this scenario. Yeah.
Thank you.
Thanks.
I'm Yang. This is a data format running cross-modal implementation for non-top-down extrovert meditation. Now let me explain the motivation. In most fear-based imitation learning, touch merely becomes decisive. We want to do two problems. Welcome in the understanding. So the conclusion. Building on that idea, our method is a unified layer-to-tail framework for textual management. We use cross-attention layers with there are several filter modes from the baseline. The other field due to a lack of total severity, such as not watching those differences of insufficient with so that's all. Thanks for listening.
I'm not sure if one of the authors here, they contacted us before that there might have been some problems with immigration. There might be poster, I'm unsure. Just check it out when you go to the poster session. Otherwise, feel free to reach out to them.
In this video, we propose a novel closed-loop pipeline that integrates interactive perception with online refined access estimation obtained from Segment Anything Model 2 based tracking. Articulated objects manipulation requires precise object interaction. Previous research employed interactive perception for manipulating articulated objects, but typically, open-loop approaches often suffer from overlooking the interaction dynamics. In this study, we propose a novel closed-loop pipeline integrating interactive perception with online refined access estimation from segmented 3D point clouds with SAM2-based tracking. Our pipeline consists of 3 core modules. In the interactive perception module, the robot applies any interactive perception methods to manipulate the articulated object, creating a slight displacement. As the robot initiates the manipulation, the camera periodically records dynamic RGBD data. In the tracking and segmentation module, we continuously track the object using SAM2, proving mask for extracting the corresponding portion of the reconstructed 3D point cloud representing the object from the dynamic scene. By subtracting the oriented bounding box, OBB, of the entire cabinet in the first frame, we obtain the motion part of the articulated object. In the axis estimation and manipulation module, the axis of motion is explicitly calculated based on the OBBs of the active part point clouds, which is subsequently used for the online axis estimation refinement. Please check our main paper for more technical details. We evaluate the performance of door opening and drawer opening tasks under scenarios involving wide manipulation ranges. We incorporate the state-of-the-art RGB MANIP as the fundamental implementation of the interactive perception module in our simulation experiment. Quantitative results of basic tasks illustrate that both our method and RGB MANIP almost outperform other baseline approaches, while ours consistently surpasses RGB MANIP in basic tasks. For more challenging door opening and drawer opening tasks, granular results clearly demonstrate the superiority of our online axis estimation approach over traditional methods, especially in tasks that demand precise axis-based control. We visualize the manipulation process with online axis estimation refinement. The initial estimated axis is represented by a lighter shade of red, while the progressively refined axis is indicated by increasingly darker shades of red. For real-world deployment, our method retains robust despite the presence of noise in real-world point clouds. For failure cases, our method relies on the quality of SAM2 segmentation. For example, the robotic arm may occlude part of the cabinet. Besides, our method affected by the initial displacement. For example, too small opening lead to inaccurate estimation at the first attempt. For limitations, future work are expected to introduce more efficient pipeline for real-time deployment and generalize to higher DUF articulated objects. Thanks for watching.
All right, I'm not sure. Is one of the authors here? No. Okay, then maybe they're there during the poster session.
This paper introduces equivariant neural augmented object dynamics, which can be learned from few interactions. We propose a novel approach for combining physics simulators and graph-based neural models that facilitate sample-efficient learning of object dynamics from human-object interactions. Given a small amount of human-object interaction data, we learn an equivariant neural augmented graph dynamics model named PyGraph, which facilitates downstream robotic manipulation planning using model predictive control. PyGraph can be deconstructed into two key layers, namely a physics-informed model where the object is implemented as a spring mass system, and an equivariant graph-based neural network which, when learned, guides that simulated object to realistic poses. Given a human-object interaction pair during data collection, we decompose the object into a fused point-cloud point from object segmentations and construct the string mass system from its initial state. To facilitate one-to-one particle correspondence across interactions, we track each particle's movement over time by applying external forces to each particle in the direction of its closest fused point-cloud point at every time step. The object state, represented as a spring mass system, and the inferred push action act as inputs into an equivariant graph neural network, which exploits symmetry and object motion along tabletop interactions. The learned equivariant graph dynamics model is capable of predicting next states given push actions. However, it has no guarantees on physical feasibility. As error accumulates over time, the dynamics model does not preserve shape, nor does it adhere to interparticle penetration constraints. To combat this, we guide a string mass system towards the model outputs. This guidance framework is implemented as PID controllers, which apply external forces to each particle in the direction of the model output, similar to the external forces calculated in point cloud tracking. By guiding particle simulators in this way, the resulting dynamics model is one that can be learned from few real-world demonstrations while maintaining physical feasibility over long horizons. The underlying spring mass system is implemented in Warp, which allows us to simulate 1,000 concurrent action trajectories and iteratively optimize for actions using model predictive control. We validate the utility of our dynamics model on tabletop manipulation tasks for T-block pushing, rope reconfiguration, cloth lifting, and more, using only 5 minutes of human interaction data per object for training. These results validate that our dynamics model is able to accurately and efficiently learn from few real-world human interactions using only a fraction of data used in previous works. We see failures in our model where it correctly plans to move the object in the correct location, however the orientation of the object is incorrect. We believe this occurs due to the fact that our performance measure is the chamfer distance between the object and goal point cloud, which does not have a direct one-to-one correspondence between particles. In the future, we would like to explore how attaching Gaussians to each particle and rendering them affords more accurate planning with images as our goal measure. Additionally, our method is mostly limited to non-prehensile motion tasks due to the fact that gravity can break equivariance for 3D manipulation. In the future, we would like to explore how sub-equivariant models could combat this limitation. Thank you.
Hello, hey. We have one question. Why does equivariance break in 3D?
Yeah, well, if the object is falling, so I feel like if you're moving an object, and let's say you let go of it, it may not fall. There's like this whole like literature on semi-covariant graph neural networks where like three-dimensional motion is not necessarily like symmetric. I can't think of a good example, unfortunately.
Okay. Thanks. I'll come to the poster.
I also have another question, which is you have these mass springs to enforce some with the PID, the shape, but do you think this could have some drawback for elastic deformation? Like, for example, it deforms elastically your object, and then you have these constraints that you enforce.
I'm not sure I understand what you mean.
So I guess these constraints work in terms of maintaining the original shape. Sometimes like you you have a cloth and you stretch it. Then you want these springs to actually deform.
Yeah.
Would this be a problem in your current
Yeah,
framework?
you would have to rely on actual neural network to like learn that deformation, and then the spring mass system would stretch to like reach those model outputs. But it's only, yeah, there's certain like assumptions I'm making with like how the actual like object can move, right? So if it's like permanent like breakage or something like that's something like a spring mass system traditionally like cannot simulate. So yeah, there's like limitations into like mostly I'm using the spring mass system for like this like to maintain shape over time pretty much.
Thank you.
Thanks. Does paper introduce it to
Hello everyone, we are Namingri Laboratory in Chiba University. For now, we'd like to present our research, real-time tracking of origami with physics simulator considering fault lines. Manipulation of a deformable object is a difficult problem for robots. In particular, paper is a difficult object to be manipulated because, in contrast to cloth, it has bending elasticity and plastic deformation. He has been studying robotic paper folding and succeeded in very triangular forms. However, the paper shape was not accurately estimated, and it was difficult to achieve more complex folds. Here's an overview of our paper shape tracking system. We mount inter-rear sense RGBD cameras at 5 viewpoints, and the Vision PC runs a real-time digital twin simulation with two processes called tracker and simulator. We extract the paper region from the RGB image and obtain its shape as a point cloud. In parallel, a physics simulator predicts the paper's 3D deformation. We registered, measured, and simulated point clouds using coherent point drift. The simulation method uses substep extended position-based dynamics. The paper is represented by a mass link array model, where each link includes a spin and damper. To capture irreversible deformations such as freezes, plasticity is incorporated into the springs. However, this model presents a trade-off in plasticity. Increasing plasticity makes the paper deform more easily, but it also reduces robustness to input noise from the tracker process. To resolve this trade-off, we localize plasticity. We first perform node clustering to detect fault lines as cluster boundaries. Clustering uses k-means with Mahalanobis distance, constrained so that clusters form approximately planar distributions. We then determine whether a link lies on a fault line from the cluster labels of its endpoints and apply plasticity only to links on the fault lines. For evaluation, we conducted real-time paper tracking in the physical setup. The manipulation follows square-based folding. As a result, we successfully tracked a full sequence of folding. However, because collisions are not modeled in the simulator, model tunneling occurs. As feature work, we will address the model tunneling problem by optimizing system parameters and accelerating processing. For more details, please visit our other session. Thank you for watching.
Okay, thank you for the video. So I have a question. As we can see, CPD sometimes suffer from severe registration error. So do you have any idea to improve it?
So one more time, please. I didn't hear clearly.
Sorry. So you didn't hear me clear?
Just simplify question, please. So
I mean, I think you have shown some problem of the CPD. Its registration is not very accurate in the real world. So do you have any ideas to improve it?
Yes. So the this CPD program, simulated program, which one? You can see the program in registration or simulator. Uh, I think the program is model tunnel has offered. So we try to handling considering creative constraint of a simulator, and it's improved. It can improve the tracking, uh, yeah, tracking and labels performances. So the, is that my is that answer of the question?
Okay, thank you. I think we can read that more during the poster. Thank you.
Yes, thank you so much. We have one more last short video from our sponsor, Lightner, before we send you to the slightly delayed coffee break. Yes, this was a long time to stand here in silence. Questions today outside with some demo. So now it's time for the poster session. Since we're slightly over time, we're going to extend the poster session to like 5 past, maybe 10 past. So just assemble back here for the next invited speaker. For the digital participants, the posters are also available on the website. And you can find the posters if you go twice left. And then we have 2 allocated poster zones. And yes, now it's time for coffee and posters. For the presenters of posters, please come back at the end of the second part because we have the award ceremony for best paper and best poster award. So see you all again after the coffee break. Sir.
Hello, Ollie. Yes. Hi, how are you doing? A little bit stressed. How are you doing? When did you arrive? Here? Oh, you mean, I thought you meant in Toronto. When I went to my son. How was your flight? What the place? I actually the office was narrative. I put my thank bro. How are you doing? Hello on. Hey, hi. Yeah, I know. You're like the first name I knew of, like a collaborator on the. Hey, hi. Hey, hi. Oh, say hi to Mother. This is kind of run out. And especially this format, because they are really tolerate. So hi, are you guys out? Yeah, nice. Bring that English. So you can enjoy. Spirit, I was breaking this. Oh, pretty good, yeah. We couldn't even finish. It's not. It's right. Yeah, that's one. Yeah, I know. Yeah. We don't know how you get yeah. Sorry, yeah, I'm working now. Yeah, good. Yeah, I hear almost well, leave of absence, indefinite leave of absence. It's very fun. Yeah, it's good stuff. People discovering statements, but they're calling something else. Right. Perception for this stuff is the most painful part. It's like, this is story. Well, somebody did extend it now, so that, that, this is the people that maybe you can children, this is stuff, maybe it's not changing, maybe you are, there's, and on here, so I call it for you. I think it's I think this means that it's hours and she have it's full. Yes, the one will share. So this will go on is in 1,000 in 20 minutes. It's from the school. I mean, that's it. Myself, it's very like time direction of 9 hours. You have to it's yes, so you're going to like how come those were on how would you figure it out with your home? I usually put humorous traveling with bond and it gives you kind of these performances so it's that it's making it and it doesn't the type of this film really well so open years and one of those things also those that
You want some coffee?
Yes.
And let's read. Alright, listen. In fact, this is their thing, so you can also take whatever you want. Or because it's 30 days the coffee. You want chocolate?
You're talking like very lots of simple having that. I really miss about stuff. From yes, very much you were here to yes. Why don't you help the efforts? You have the site object center. Right, so you can message it around work on the systems.
I'm interested what do you want this? If when it were in the journey, so I was the first impression from last week. So now that's simple. I think this is like a very nice feeling. I just love your quickly. And especially like screen presentations.
That's right. Guess what I
No, like that.
This is
Don't
yeah. Yeah. How I think yeah. Very nice to meet you and really appreciate how also invitation. Yeah, I'm so excited to very pleasure and honor this way. Thank you. Yeah, thank you for the opportunity. Hi. Yeah, thank you so much for inviting me. Thank you, Holly. Yeah, really appreciate the opportunity. And I would say we are very excited in the future, continue to sponsor, to support whatever way that you guys need. No, seriously. No, seriously, like we need to get the beyond rigid body to work.
Yeah.
So this is the most important thing. This should be the session, the workshop. That like this should be the most important workshop in CoRL, in my opinion.
We're glad for doing
No, seriously, like this is the most important one. So I really appreciate it. Yeah, and also I want to. So basically, I will find some time to introduce you to the evidence center on that. Oh, well, you don't know your own. Oh,
George.
yes. I know. Oh, just continue.
Yeah, exactly. I actually did not work the 3D team, like basically. But yeah, it's good.
Yeah.
Sections. I work, but yeah,
Yeah.
I want to be friends. So for me, it's an environment where there's a lot of new things. I really want to be open for collaboration. So of course, I need a lot of different projects. I really like flexible representation learning and connected perceptions. And I think that it's since I have it's a lot of implementation, so I like a lot of that topic. But who knows? I really would like to know what it's like. Yeah, exactly. Except like to keep the formal interactions and keep that. But I'm sure there's a easy step for this as well as to explore more interactions. I mean, once you took me over something there, to step out into my comfort zone and make comments. I still don't have that question. What makes sense is making it.
Fair.
So this is some fun. Yes, yes. We're going to get it as well. Spread the love. Stuff.
I don't know. Actually, I know. Yeah. It's these most forward in what we're solving. It's a really cool function over it's big all the notions of me. And all the talks not in us. Yes, but with plans, it's easy to access that balance to improve the general process. Neutral pure solution to what I see here. Almost so it's this call so we use process of incidents or hospitals, spaces, and yes, resident. So that's like everything that is doing this research online. It's like share options here. So for me, it's actually all 28 slides. They can no, it's your perspective. That's until yeah, that's like what could go one line. Or I have a few shares for you all. Also, so sometimes I use standard back. So, I think it looks similar. It's the same, right? Before.
I think it's better. It's just the features are a little bit fuzzy now.
I guess. I guess.
Yeah, I think that's a lot better. Actually.
You mean one million is position. So now it's just go to this. It's a very restriction. Maybe you could just.
Can you maybe show like a couple slides?
Yeah, absolutely. Looks okay, right?
No, I saw.
Sure, that you know, yeah.
All right, everybody. We can all have from a coffee break. Hope you're all refreshed to a little bit of we had some engaging talks at the posters. Probably a few people are still stuck outside, but I think they will come in after they're done. So I'm excited to announce our next speaker, Yun Lee, assistant professor at Columbia. Before that, he received his PhD in computer science from MIT, was a postdoctoral fellow at the Stanford Vision and Learning Lab, and assistant professor in the Department of Computer Science at the University of Illinois. Yes, and then I think the stage is yours.
Yeah, thank you for the very kind introduction. And super excited to be here to talk about some of the things we've been doing with mobile objects with structured word models. So for today's talk, I will actually also talking about some of the things I'm personally very excited that has many of the industrial expositions like Automate or ProMat. You'll be impressed how many boxes you'll see, just oceans and oceans of perfectly shaped box. So that is the current state of the actual industry scenarios. So that is something we want to go beyond. We humans actually can do many more tasks interacting with deformable objects, go beyond what is capable with the current robotic systems. And one of the key missing pieces that I would like to argue is this kind of intuitive models of the world. Basically, we human can predict how the environment is going to change if we apply a specific action. And this predictive ability applies to, for example, how the dough will change its shape and how the onion pieces will move around. It applies to many different kinds of scenarios that allows us to plan our behavior. Specifically, we have the world. This world will give us some kind of observations. And within this kind of planner, we have these intuitive models that takes the observation and actions to predict the evolutions of the systems. And the result of which will help the planner to predict its actions in order to get the world evolve in a way that the system wants. So over the years, there has always been discussions and debates. We have also heard people earlier in the morning, they're trying to model the dynamical systems of deformable objects. And if you look at the spectrums of methods, you realize there's one axis, let's just add more and more learning. So these directions, I think some of the recent results, like Genius 3, really show some very impressive results. What you are doing is just to do action condition 2D video predictions. On the other hand, obviously it will be more physics. There's NVIDIA Warp that is trying to use mathematical models to predict or modeling the dynamics of different complicated systems. And difference, on the learning side, obviously is applicable, can directly benefit from data. But the generalization capabilities of this type of model is heavily constrained to the data you actually use to train your model. So for Genius 3, highly likely it's trained on oceans of game data. So it doesn't really generalize to more complicated physical interactions that are not seen. And for the NVIDIA Warp, it is very generalizable, but it's restricted to the set of physical interactions that can be expressed by this kind of physical model, and the flexibility of which is quite limited. So for a long time, our lab has been trying to get the best of both worlds, the best of both learning and also the physics, something in the middle. So over the years, we have a serious work that's trying to build this called graph-based neural dynamics models. And basically using graph neural network to model the dynamics of a diverse range of deformable objects, like a fluids, rope, clothes, stuffed animal, interactions between them. We have a serious work including the best system papers awards, at CoRL, that are making dumpling out of a dough, multi-object interactions shown on the bottom left, as well as granular manipulation shown on the bottom right. This all shows the power of such type of neural dynamics model based on graphs. And very recently, we also have a science robotics review paper that reviews the series of investigations over the past decades or two that are trying to nerd dynamics model from the robot's interactions with the environment and using this nerd dynamics model for the robot to do physical interactions. And the structure of which actually built on top of my PhD thesis. So this paper has some special like personal touch with me. Highly recommended if you are interested in this lines of work. So then what we are asking is that after we have done this series of work on graph-based neural dynamics, like what's next? So what are some of the directions we want to push forwards in making this type of model like even more powerful? So obviously, we want to model more complicated tasks and objects, some heterogeneous type of interactions between different types of materials. And I'm really trying to answer the question, how can the model benefited from the current large-scale data collections? How does the performance of the model scale as we extend to larger and larger data, like OpenX or Joyce, and really giving us this scalable data engine and scalable evaluation engine. And that's the key questions we're hoping to answer. And then what we're trying to do is look at the recipes. Some bit of learning, some bit of physics, and what is the nice marriage between them that can give us this scalable but also generalizable recipe. So first I want to introduce a recent work we have been doing called face twin. Specifically, what we do is to build a digital twin of deformable objects. For digital twin, what we mean by we capture the geometry, the appearance, and also the dynamics of this deformable object. Here what you are seeing on the left are just a few seconds of real-world observation. So given a few seconds of real-world observations, we're doing the reconstructions of the objects, capture the appearance of the objects. The geometry is shown in the middle, where we have these points describing the overall shape of these objects that are also tracked over time. We also have red points overlaid on the human hands, indicating the reconstructed actions we reconstructed from the video. On the right, what you are seeing on the foreground is essentially open loop, action conditions, 3D video prediction. Basically, we replay our reconstructed action on the digital twin and generate the video from the same viewpoints as what we have for the observation. We render the video and overlay it with the original video. You can see the overlay between the foreground and background, indicating the accuracy of our face twin. Specifically, for the space twin, the construction of which consists of 3 camera views shown on the top left. The 3 views basically give us the reconstruction and tracking of these deformable objects. And within the inner structure of this model, we use a physics-informed dynamics modeling systems for these deformable objects. And the structure we use specifically is built on top of spring mass. And on the right, we show the formulations of our optimization problem. We're optimizing over the geometry, the motion, and also the rendering of it. Well, the rendering is done using Gaussian splatting. The motion, the supervision for the motion is coming from code tracker fused from multiple camera views. And the geometry is actually got from a model called Trellis that is doing single image 3D reconstruction. So many of the success of these constructions is actually coming from the success of the progress in the vision foundation models. And after you have the digital twin, what you can do is to use keyboard to randomly interact with it and give you this action condition 3D video prediction to predict the evolutions of the system. What you can also do is to apply the same pipeline on a wide range of objects like stuffed animal, rope, clothes, etc. And again, I'm a roboticist, so I will always want to place this type of model near robots and to see what happens. In this video, what you are seeing is on the top left, we have a teleoperation setup, a person teleoperating a Gallo interface to collect the teleoperation commands. And on the right, what you are seeing is we first replay the collected actions on the real robots shown on the bottom left. We also replay the same actions in an open loop manner on our digital twin, which is shown in the foreground of the screen. So this video essentially shows 2 things. One, the foreground of this digital twin rendering in an open loop fashion aligns very, very nicely with what's happening in the real environments, showing the accuracy of our face twin. And second, This is very clearly that our phase twin is running in real time because we implemented everything like on GPU that benefited the accelerations in terms of computation. Then what you can have are videos like this. On the left is our digital world. On the right is the real environment. Exactly the same robot trajectory running the digital world on the left and the real world on the right. You can see the strong correlation between both the dynamics and also the appearance of the rendered video that shows the qualities that we want to strive to achieve. So you have seen, like, hear me saying the words correlation again and again. What I mean by correlation is we want the results we got from the digital world correlates with the results we should expect from the real world environments to really go towards this scalable evaluation engines. So the reason we want to do it is really coming from conversation I have with friends at Google DeepMind. So these are some of the Aloha systems they have at Google DeepMind. And what they've been telling me is that evaluation is a huge bottleneck for them. And this actually is a key difference between developing large language model and robotic foundation model. Because for large language model, evaluation is so easy and so scalable on the cloud. For evaluating like a robotic foundation model, currently people still only relies on the real world evaluations. So for Google, we probably think they are maybe evaluating hundreds, if not thousands of checkpoints every day. But in reality, they can only evaluate just a handful of checkpoints, and they have to wait for 2 days for the results to come back. And my friends, their exact words was, we have large enough budget such that we can still make progress. So I'm pretty sure whatever they mean by progress can quickly diminishing when they move to more complicated, like a larger scale environments. So then, like, we basically spend a lot of efforts making sure our phase twin is easily constructed by just taking videos from the environment. Here is a person just like taking video scans of the robots. On the right, we show our reconstructions of the robots, together also with reconstructions of different kind of objects. So that's how we're building the appearance model and the geometric models for different kind of deformable objects. And then obviously what we need to align are the rendering parts. On the top row is our real images. In the middle row is the direct rendering results from our rendering engine. Obviously, you have to calibrate the color such that the rendered image match the real world image. You can see like how the first row and the last row, one in the real, one in the digital worlds, aligns very nicely with each other. And then what we can do is to do the constructions of this kind of digital twin. On the top row shows the data we use to identify the dynamics of the objects. Again, just a few seconds of real-world interactions. On the bottom, we're showing an open-loop predictions of our phase twin, overlaid with the original video, showing the accuracy of our digital twin. And then putting the things together, what you can have are the simulation states shown on the left, and also the real-world rendering states shown on the right. And to show it in a sliding window manner, you can see how the rendering quality and the simulation qualities is evolving as we are applying different kind of rendering techniques and color calibration techniques. And then let's put this engine into use for evaluating visual motor policies. Here is one simple policy we're going to evaluate. Here's the robots running in the real environment. They're basically routing this rope into the clip. And here are the camera views the robots are getting. On the left is a third camera view. On the right is a wristed mounted camera views. So those are the two exact inputs to the visual motor policy, and the robot is able to accomplish this task. And here is how exactly the same policies will be able to do this kind of rollouts in the digital world. And on the left is the rendered view from our digital twin. On the right is the rendered view from our wrist-mounted cameras. So I want to emphasize here, the policy is trained only with real data. There's no sim and real co-training at all. The model is only trained on with real data, but running directly in our digital world and shows the state-of-the-art correlation between the digital world and also the real-world environment. There are just some more visualizations showing the performance. Again, these are not real videos. These are all rendered videos from our digital twin. On the top, showing a packing task. On the bottom, showing this T pushing task, such that you can align this T with the target shapes and the pusher will move to the dots on the back. So meaning the policies like trained only with real data can actually show success performance also in our digital world. Here are some more results showing the side-by-side comparison between the digital world shown on the top row and the real environment shown on the bottom rows, just to show you how the performance, how the behavior can align very nicely with each other's when you have exactly the same policy but running in different kind of worlds. And what you can do is you use a digital twin to do scalable performance evaluations. You're just showing some kind of different initial variations, and we can run the policies on top of those different initial variations, which allows us to evaluate how good the policy is and whether this policy can be successfully accomplish this task for this specific initial configuration. And we show very, very strong correlations between the policy's performance in the real environment and also in the digital world. On the horizontal axis will be the success rates in the real environment, and on the vertical axis showing the success rates in the real environment. So among all the tasks, we all shows correlations that are over like 0.9. And we are not like just like using our own policies. We are evaluating off-the-shelf policies like ACT, DP, or for example Pi0. Those are some of the policies we evaluate, and out of the box, using our engines, we can show some strong correlations. And we are actually being quite like rigorous in our evaluation protocols, both in the real environment and also in the digital world. Really inspired by some of the recent papers, specifically from Toyota research. They are really trying to set up some kind of standard and benchmarks on what are the good like empirical practice when people do real world evaluations. To show you one example of which, for example, we actually have a set of initial configuration that is aligned between sim and real. And we do real world evaluation. We align this kind of deformable objects according to some overlay shown on the top left, such as we show fair comparisons between simulation and real world environments, trying to reduce the variations inside these evaluation protocols as much as we can. So these are some of the empirical treatments we do in order to really giving us trustworthy results in establishing the correlation between simulation and the real world environments. And compare with Isaac, like our twin, like because of all the efforts put behind it, we have much better alignments on the appearance side and much better alignment on the dynamic side. So our performance will be much better correlated with the real environment compared with, for example, Isaac. And the evaluation result can also help us to, for example, pick checkpoints over training different training routes. Here we just show like different combinations of the task and also the policy. The horizontal axis shows different training iterations, and the y-axis shows the success rate. The orange line shows the results in the real environment, and the blue line shows the results in our digital world. You can see this kind of alignments on the overall trends between our methods and also the evaluation results in the real environment. And our digital environment can be very effective in helping us identify what are some of the promising checkpoints we should actually pay attention to. For example, in the first sub figure, you can see the best checkpoint is not happening at the ends, but maybe somewhere in the middle. And our digital twin is very effective in identifying that specific checkpoints. And in this paper, we have also been able to do a number of evaluations on different ablations of our system. For example, we show that the physics optimization matters, and also the color alignments also matters. Those all contribute to the final alignments and correlation we are able to achieve between sim and real. And furthermore, we are also building some additional engines that allows us to model elastoplastic objects like cardboard box. We not only have this engine that can simulate this kind of elastoplastic motion, but we also have a systematic pipelines that identify those parameters, such as the simulation and real world, they align very, very nicely with each other. When you put a robot there, here is the type of correlation you are able to achieve. On the top left is simulation. The top right is what's happening in the real environment. So what's inputs to our engine are the initial states of the cardboard box, as well as the actions. The top left, I want to emphasize again, this is not animation. This is simulation. And this is the levels of alignment and correlations we are talking about in building this scalable evaluation engines using simulation that really indicates how a policy should perform, will perform, and where that policy will needs to be improved in the real environment. So this is about our efforts in going towards like scalable data and evaluation engines. And I just saw Emil come in, and this type of like evaluation engine is actually integrated into Mojoko, such that this kind of correlation you are also able to use within the Mojoko like interface. And besides using this kind of more physics-based approach, we have also investigated an approach that's more on the learning side. And I know I'm close to about time, so I'm just showing you some kind of demos in using like a more learning-based approach in learning action condition 3D video predictions. We have different actions conditioned by our predictive engines that allows us to do action condition like 3D video prediction. So just to summarize, so a lot of things we've been doing is really trying to identify the recipe, combine the best of learning and the best of physics to get us this recipe to really build this scalable data engine and evaluation engines that are gonna unlock some of the key bottlenecks we are facing by the entire community in going towards general purpose robotic intelligence or robotic foundation models. I just thank all the collaborators and also funding agencies. Without them, it would be impossible to do all the work I've been able to do. And I'm happy to take any questions. Thank you.
All right, thank you for this really cool talk, and also thank you so much for staying really good into time. And now we have about 5 minutes for questions, so please come forward to the microphone there in the middle.
All right, thanks so much for your talk. I'm wondering, well, first, I want to clarify an assumption that for the simulation, it's all based upon observations of actual, say, instances of objects that you've seen, right? And so the question is about generalizing to novel objects, and are we on the right path here to say, you've got the sloth and the rope, can you infer a model of a stuffed snake, right? And then incorporate that into, first the evaluation, but then eventually I'm thinking about the role models that you actually do for your manipulation.
Very good question. So currently, we still rely on some real-world data captures. And for example, appearance and the geometries, some kind of still videos, some kind of still images, or like videos around some still environments is good enough to capture the geometry and appearance of the environments. But you want to identify the parameters for like deformable objects, you really need some kind of video in order to identify those kind of parameters. So we already, because of the physics-based priors we added to these systems, this whole process is already very simple efficiency, very simple efficient. Just a few seconds of real-world interactions. We're going to identify all the necessary parameters to establish this correlation between the real environment shown on the top and the digital world shown on the bottoms. So possibly you are curious, how does this model generalize to different kind of instances? Let's say you have one type of cables, like an HDMI cables. But when you place the order on Amazon, depending on the specific instance you get, the dynamics, the rest shapes are all going to be different from each other. So what we are hoping to achieve is, again, just a few seconds of interactions with that object, which is nevertheless we have to do if your robot has to interact with that object. Those should be enough for us to identify and build this digital twin for that object.
So to clarify, when you say a few seconds, so you thinking of a scenario where you actually start to pick it up, you build it in real time and use it, or?
That would be the goal. That's like online adaptation parts. We haven't really resolved that. Currently, we still takes maybe 30 minutes, an hour to do the overall optimization for all the parameters that's necessary for this kind of systems.
I would think so.
Yeah, thank you.
Hello, great talk. So I have a couple of questions. So how do you actually do the action specification? I see this red dot, but you actually don't get the force, or it's the velocity of the red dots, or how?
Okay, so for this specific ways, what we do is for those kind of contexts, we essentially move the ND factors closer to the particles that are representing the particles that are considered to be the neighborhoods of these grippers. And when they are getting close enough to each other, we can rigidly attach them together. So this is a very hacky ways of doing the interactions. That is what we did actually for the initial phase twin. Basically, if you have a mouse, you basically assume those points are rigidly attached to your keyboards and you are moving them around. But later, as we move into this more scalable evaluation engines, what we did is we are able to decide whether they are in contact or not. And when they are in contact, we have some kind of local friction models such that you will be able to pick up this slots to insert that slots into the basket. And when you are open the gripper, you are able to, for example, release those slots into the basket.
Got it, makes sense. And I noticed that the shadows are actually kind of rendered a little bit. How do you do that?
Okay, that's a very good question.
Yeah.
So here in this video, the shadow is fake. We didn't really reconstruct the lighting conditions. We just artificially and manually added some shadows there.
With depth maps.
With depth maps,
Yeah.
yes.
Okay, I have one more question, which is that when you scan these objects, for example, the other side of sloth may not have been visible. So I noticed when you capture the rope that it kind of hung, so you actually see all of the sides of this. How much of this do you think is a problem actually?
Okay, actually for the reconstruction of the slots, we also hang it up. And such that we can have the back side of their slots. So you are right. So currently we are being a little bit creative or ad hoc in how we do the reconstruction of the objects, but how can we build a more systematic pipeline to do digitalization of those objects is definitely really an interesting question.
That's actually quite non-trivial because you got to figure out how to hold it and then make sure it doesn't appear in the reconstructions.
Exactly. That's not only about the appearance and the geometry, it's also about the dynamics. So that's why you can see in many of the videos we show, it's actually the person who is interacting with the objects. That is the most effective ways of reviewing how the object might be interacted, like during the robots interactions. So the relevant data is also matters.
It would be really cool to do it all together.
But feel free to reach out to Yunsu or ask the question if it fits later on during the panel session. All right, I'm gonna skip the switching of the laptops for now, but I'm happy to announce our next speaker, Steve G. He is the founder and CEO of Lightwheel, a company which focuses on simulation and synthetic data infrastructure for embodied AI. Hopefully that the autonomous driving simulation at NVIDIA and Cruise, where they build large-scale synthetic data pipelines. He holds a bachelor in physics from Beijing University and a PhD. Happy to introduce Steve.
Do you need software? No, I don't need software. Getting there. Okay. Cool. So thank you so much for Holly, for Alberta, for everyone's invitation. And today, this is really my great honor, pleasure to be presenting in CoRL in this workshop. Yeah, and my topic is how Lightwheel accelerates non-rigid body tasks with simulation. So I was planning, so usually I'm in the more energetic, passionate side. But after I heard about Yunzhu's talk, which is really awesome, by the way, and I found out maybe I should be presenting in a more chill side so that I can contrast him a little bit. Anyway, so we at Lightwheel, we really have a strong conviction in simulation. We really think that simulation is the ultimate key to solve the embodied AI data problem, solve the embodied AI RL problem, to solve embodied AI tracking problem, right? And I know every researcher has really great research on R&D that's always innovating. But my philosophy is we have some product solution already there that we can make it work. So today I'm gonna talk about our philosophy and how we make it work. Cool. So for our customers, we only serve, I would say, almost all of the world's most top companies working on embodied AI, working on robotics. NVIDIA, DeepMind, Stanford, really like our great honor to work with behavior team, Figure, Genesis, and also some of the leading robotics companies in China. And yeah, so here's goes to the first thing in that I have a strong belief. I really believe in data pyramid. And in order to achieve data pyramid, I really see simulation, synthetic data is the key, right? So there's no way we can run away from simulation. We have to face it. We have to solve it. Then I would say our approach is we are starting with rigid body, right? And I just want to showcase to you how we started with rigid body, how, in my opinion, we have already solved the rigid body simulation problem together. That includes about the sim-ready size, that includes about the data collection, that includes about the benchmarking, that includes about RL, everything, right? So we start with this sim-ready size, and you see it is very highly, like I would say is visually accurate, but most importantly, physically accurate. You know, the joints, the collision, the multi-friction, and also the magnetic feeling, magnetic sealing, all the forces, they are very accurate, right? And we have a very mature pipeline doing that. And through this pipeline, we are actually guiding the real world physics, right? Through all those data collection equipments there. I really see that basically for the simulation problem, there's no way we can leverage AI, we can leverage automation to fully automate this. There must be a lot of operations, right? How to get the real physics into simulation, right? We have done that part, right? So we have already basically get the real physics sensor in the real world, but also get a simulated sensor in the simulation world, right? And also benchmarking between the real and also the sim, just to make sure every sim-ready assets that we carry, they're accurate, right? And also there is a large scale of them. It's not only one fridge, it's not only one house, it's many of them with a relatively accurate diversity and distribution. And after that, this is our standard, right? So we make sure they are physically accurate. We make sure that they can support real operations, right? So it's pretty much like if you build a new house, you know, and only until you live in the house for 1 month, you can fully check everything is fine, everything is working. And for the 1 month, probably like it will be terrible that you found out some of the things are not working. Same thing for simulation. We are actually making a home for robots. So we need to let the robot live in the home, right? To test it, to make sure that it is at fully productive scale. Right? So that's our purpose. The third thing, which I think is the most important, is reinforcement learning. Right? Simulation is not only for data collection, it's not only for benchmarking, but for large scale RL. And I'm not talking about running RL in 14090. I'm talking about large scale reinforcement learning fine tuning for VLAs. We are already working with our customers on that. You know, our customers leverage our solution to scale for hundreds of GPUs for RL fine-tuning of their VLAs already, right, in simulation. Right? So I just want to showcase to everyone that simulation already works. It's not like there's a hope that simulation can work, it already works. And also we are doing a lot of open sourcing things there. Because I really see that there are a lot of great benchmarks. For example, YCB, Libero, RoboCasa, and also behavior. They are done by students, they are done by researchers, but they are not at production scale, right? So we refreshed YCB. So you can see for this refreshed YCB, it is carried in both MGCF module code and also USD supporting SSIM. It has out articulation. It even solved some of the deformables already. So we just open source it, collaborating with Professor Sid from University of Washington, the original co-founder of ICB. We already open source it. And all the YCB, like the YCB assets, they have done the data, like the teleops quality control, the reinforcement learning testing to make sure that they are fully useful, right? And that we are actually open sourcing the Review Refresh Libero and also RoboCasa pretty soon in next month. And the benchmarks, they are open source. They will not include the sim-ready assets since also the data collected, right? So for every researcher to use. And through all those things, ISS, we are doing large scale data collection, right? Through all those data collection methods, there, AR, VR, skeleton, right? Already there. And I will just make it quicker to show you the world's largest synthetic factory. So this factory has 250 people, but we have another factory right now setting it up already. And our goal is by next year, the same time, we will reach about 5,000 people globally collecting data in simulation, right? The major data we are collecting is through still rigid body articulated tasks, but actually we are collecting more right now through deformables already. And you can imagine some of the top robotics foundation model companies, they already leverage large scale of data already. And also very happy to work with behavior. So behavior challenge also leverage part of this data. Cool. And after that, basically, we leverage the data, we leverage the foundation model, we accelerate it. We even further fine-tune the foundation model that we supported, right? Left-hand side is simulation, right-hand side is real. We deployed real robots in the real functions already. So this is already done, right? So I just want to showcase to you that how we get something done, fully designed ready, in rigid body already, right? So now we get into the non-rigid body problem there, right? Still, non-rigid body is much more difficult than rigid body. We still need a lot of research. So you are in the right topic. I would say the most important topic right now for robotics to solve. Right, but still, I want to showcase to you what we can already done through SSIM, through Newton. Right, the left-hand side is SSIM, the right-hand side is Newton. Folding code is totally fine. We can collect a lot of data for folding code even in real time already. Right, and also we are already on deformables in different type of industrial use cases there. For example, cable, wire, in manufacturing. The top right-hand side is basically the surgery, like in medical space. Still, I would say the surgery in medical space is a little bit R&D still, right? But the left-hand side is lower in the corner is basically cutting sausages, like leveraging the different type of tools there, and then the bottom right is basically picking up strawberries. And this can fully support not only in data collection, benchmarking, but also reinforcement learning. We actually help our customer to train our policies in simulation through the deformable, through the sim-ready assets there, and deploy the policy to them. And also, this is a pretty cool task of leveraging the robots and to close the curtain, right? So the difficulty there is a combination of deformable and also rigid body. And we can already handle it. And then we are thinking about, you know what, we want to introduce something more ambitious for the industry because I heard that a lot of people are talking about, hey, simulation couldn't handle deformables. There's still a long way to go. So we just want to showcase to everyone that simulation can already handle deformable through a large scale task. So we are actually working on this. It's called a home. So basically a home of all deformable tasks, all deformable related tasks that you can think of, and only through the robots. But definitely also the expert robot that has the movable base. So we already have some early results there, you know. So all the different type of tasks already. So basically, more more tasks, more things will come through this initiative. But our goal there is we will open source everything. We will open source the sim-ready assassins, we will open source the data collected and also the benchmark, right? We hope that through our work, you know, we can really build faith, conviction in simulation. We can accelerate everyone, you know, to leverage high quality simulation for beyond rigid body. Then basically, I want to talk about some of the problems still I see and how I think, you know, we can collaborate and maybe I will to help you to accelerate your research. The first thing there is, I really see that every great researcher, professor, you are working on the best, solver of deformable or non-rigid body to a certain extent, right? And you are trying to close your own loop there. So that is really awesome. But I really see that in order for us to get simulation to really work, the three things need to work together. The first one is large-scale data collection. The second one is large-scale benchmarking. The third one is large-scale RL. The large-scale RL, as I mentioned, the RL fine-tuning for large-scale VLAs, right? So there's much more thing than simply a solver that we need in order to get this done. We need a solver, we need a sim-ready assets, we need the frameworks, we need the robots on the framework. We just need everything. It's an ecosystem, right? So as the that we need is open source solver ecosystem. Like, because I see that everyone is working on the new algorithms to a certain extent. I really think that we need to work together here of building more open source physics solvers. The second thing is you already see that how we are benchmarking the rigid body, the articulated, through the physical forces collection in the real world and also in the simulation. We need the same thing for deformable, for non-rigid body. And in order to do that, we definitely need tactile sensor in simulation. Tactile sensor in simulation. So that's the second thing that I really think the whole industry, the whole community, we will need. The third thing there is larger scale, more diverse, high quality sim-ready assets. I think that LEGO can help, but the third thing needs the first thing and also the second thing to iterate together. We need to iterate with the software, we need to iterate with the tactile sensor together in order to get the best quality assets. Then it all goes to the fourth thing. The ecosystem is the multiplier. Everything needs to build on this one ecosystem, right? Deep down is the open source solvers, and then is the simulator, is the rendering. On top of it is the framework. And then the framework needs to support data collection, large scale benchmark, and also large scale RL. This is the most important thing. Then basically, this goes to my suggestion to everyone. I really see this is the only way it can. So I would say to a certain extent, time is not on our side because you can already see the large scale real data collection already scaling quite a lot, right? If we don't make simulation work right now for deformable for beyond average body, we will probably miss the chance already. So I really suggest that all the researchers to use which I think is the best GPU accelerated open sourcing language to write solvers, right? To write your new non-rigid body open source solver, contribute into Newton SSM ecosystem. That's the most important thing because it's not only one solver, it's the rendering, it's the simulation framework, it's the SI lab, it's everything, right? Then work with us by will. We can totally sponsor, we can really sponsor you for the sim-ready assets. If this is something really critical to help us to advance robotics, we are very open to that, right? So we can collaborate with you to iterate on the sim-ready assets since and also data collection, right? And I really see that this is the only way we can scale the high-quality simulation that can support robotics beyond non-rigid body. Cool. And so I really hope that we can work together to make non-rigid body simulation successful for robotics. Thank you.
Thank you so much for this industry perspective. Since we're quite progressed in time, maybe just one short question from the audience. Otherwise, feel free to reach out to them on the LinkedIn page. Thank you very much.
Very nice and extensive talk. I just had one question about Warp. So since you're into open sourcing, are you familiar with any efforts to make Warp run on like AMD or Apple or Intel GPUs, or is it locked into NVIDIA?
So I feel I'm probably not the best one to answer this question, and we already have the head of Warp. Now House already sitting behind, so maybe now House can help to answer a little bit later on this topic. Yeah. Yeah, but on my side, I would say, yeah, we just all need to work together. We will run out of our chance. The real data collection is already scaling already. Cool. Thank you.
Yes, then I'm excited for our next speaker, Sejun Hong from He's a Research Science Institute for General Science. And for that, he received his PhD from UCLA. His research aims to build a general agent capable of understanding and interacting with 3D environments like a human.
Hi everyone, my name is Suyan and it's my great honor to be here to share some of our research in how to build interactable digital twins of articulated words. Since it's a little bit out of time, so I will try to be quick. And I will introduce several of our recent works in two perspectives, the reconstruction and generation. So here is a brief introduction of myself. I graduated from UCLA at 2021, and after that I worked in Beijing Institute for General Visual Intelligence, aka BGI. And my research goal is trying to build a 3D thinking understanding system for general purpose agents and robots. So back to the topic today. So people and humans, we are interacting with different kinds of articulated objects every day and in different places. So in the video, we can see that we interact with the refrigerators, with the drawers, and a lot of these kind of articulated objects as Yunju and Steve also mentioned. So our goal today is trying to teach the robot to interact with this kind of articulated objects. However, it's very, very challenging to teach the robots using the real-world environment. For example, we can see that a lot of videos from the DARPA Robotics Challenge, like 10 years ago. So the robot can really damage the environment and the object also itself, right? So we need to protect the robot. And one way to protect the robot is trying to teach the robot in the simulation environment. And today we can see that with media, with like ISOLab, we can have very fast-speed simulation environment, but there is still a lot of questions for the current simulation environment. And we can say that using the ISOLab or this kind of simulators, we can really accelerate the interaction in the learning of the articulated interactions. We can use the RL to do the Chinese errors to have like millions or billions of steps of iterations to train models. However, we are still in lack of really high quality, realistic, and interactable object access. And I think they've also mentioned that we need a lot of algorithms to help us to automatically create the 3D asset for the robot learning. So traditionally, we have two ways of collecting this kind of high quality assets. And the first way is we can ask the artist to manually design the CAD models for us. But it is really expensive, so we need a lot of time to design the CAD models, and we need to annotate the parts and centers of the objects, and it cannot be really scalable. And another way of creating this kind of 3D assets is by the real-world scanning. However, current data sets that consist of real-world objects always require a lot of manual post-processing for this high-quality assets. So it's still very labor-intensive. So our question today is how can we build a really large-scale articulated data by our algorithm? So I talked with one of our students from Tsinghua University. He told me that we need to cost a lot to actually collect this kind of high-quality CAD models, especially for the articulated one. Yeah, maybe after this talk I can quote from Steve. Maybe we have better price, but like 2 years ago we still need like $100 for each of the CAD models, especially the CAD articulated one. So it's really expensive. We can afford that in our lab settings. So we want to have better algorithm for us to reconstruct the 3D object assets from the videos or from the interactions. I think this is a very natural way for using the vision techniques to really create the replica of the 3D assets. So we'll first introduce one of our recent work called ArcGIS. So the idea is pretty simple. We try to use the best model in computer vision and the best representations in computer vision, which currently is the Gaussian splatting. To use it, you use it as a flexible and efficient representations for building the 3D replica of articulated objects. So for people who is not very familiar with the Gaussian splatting, so here is a very brief preliminary. So for the Gaussian splats, we have center scale Bertinian spherical harmonics coefficients. We're trying to model the 3D thing and using the Gaussian splats so that we can render the Gaussian splat into the image space, and we can use that as a signal for the rendering for the supervision, and compare with the previously commonly used representations across the neural radius field. It models the 3D things by different rates. And the Gaussian splat directly model the Gaussian point in the 3D things. And below is a pipeline of how to reconstruct the Gaussian points and render them into the RGB image space to do the supervision. So this is a pretty good rendering techniques we're using in computer vision, and we want to use these techniques to boost the reconstruction of articulated objects for robotic learning. And the task of this work is we are trying to reconstruct a very accurate articulation model from the images. And the input for the model consists of two views of RGB image from state 0 and state 1. So from these two states, we want to discover the Gaussian models of the object itself and also the articulation models. So with the articulation model, we can apply rotational or translational transformation into the parts and object parts and also the centers, so we can get the digital twin of the object and we can render this kind of object in the simulation environment. But it's very challenging to reconstruct this kind of articulated objects. And the inherent reason is that we want to recover the object geometry, the part segmentation, and also the articulation parameters. And this all three factors, they are mutually affected. So it's very hard to disentangle these three factors from the two image input. And ideally, we want to get a result from the left side. So basically, we have very good clustering of object parts. And for each part, we have centers, scale, different parameters. And then we can have like the articulation parameters for each part. However, during our some empirical experiment, we found that current technology usually falls into the right side. So we cannot get a very good reconstruction result from the models. And I think canonical Gaussian and part segmentation and articulation, they are mutually affected. That will hurt the initialization of the models. So our solution here is to trying to improve the initialization model and part modeling of the reconstruction. Since we find our current model is pretty sensitive to the initialization setups, like similar to the clustering algorithm. So what we've done here is that we designed 4 steps to get a very good initialization of the articulation modeling. So first we'll train a single state Gaussians for each input. Basically we have state 0, state 1, and we have a single state Gaussian for each state. And then we can match the 2 states of the Gaussians for the initialization. And after that, we will do a clustering of the Gaussian points, so we can have certain centers, and we can assign the Gaussian points to the centers, and then we have a better part understanding of the Gaussian models. And after that, we can have a canonical Gaussian, which represent the solid or the static states of the 3D objects. And to be mentioned is that during the clustering process, which is quite critical, we use a Mahalanobis distance to calculate the distance between the Gaussian point and the centers. And we calculate the matrix M to assign the weights of different centers to its different Gaussian points. And after that, we will do a joint optimization when we have a good initialization of the models. So basically, the idea of the joint optimization is that we want to compare the random results of the optimized Gaussian into different states and compare them with the input of RGBD. And then we use the input rendering loss and the depth loss as the supervision to trying to optimize the entire process. So we can adjust the centers, we can adjust the scale, we can adjust the cluster result and also the Gaussian parameters and articulation parameters. Using a differentiable optimization process, we can eventually get the centers and get the canonical Gaussians from the two-state input. And here are some qualitative comparisons. So comparison the baseline models, our models can produce like very accurate results of the part, also the articulation of the part. And by measuring certain metrics like axis angles, like part motions, and also the transfer distance, we can see our models can actually improve the SOTA model in a great scale. And we find out that using a good initialization, for example, we have a good spectral clustering for the Gaussian points is quite critical for the Gaussian reconstruction. And after ArcGIS, we find there are still some remaining problems that can hurt the generalization of our models. So the first problem is that the current modeling still relies on the initialization process. So during the initialization process, we need a good model for the segmentations. For example, if we wrongly like segment the objects in different parts, so our final model will have different like clustering results. So this will leads to the wrong part segmentations. And we want to leverage very strong pre-trained models like the SAM models to have a better segmentation results so we can start from a better initialization to get models. And the second problem is that since the input only has two states, so it's really hard to disentangle, or it's really hard to disentangle the part that's moving at the same time. For example, in this case, we have two drawers opening at the same time. However, our model tends to believe that these two drawers are from the same part. So this leads to a lot of ambiguities from the two image setup. So one solution is we're trying to add more input to the models so we can see more multiple states from the input and we can ease the ambiguities from the input. And the natural way is trying to use the video, right? So we interact with the object in the database so we can capture a lot of interactive videos with this kind of objects and we can use that as information for the articulation reconstruction. So we just released a paper called Video ArcGIS, which is trying to extending our current baseline into video-based models. And we are trying to leverage a video-based model to help us to analyze the motions and also find consistency between the part motion and the dynamics. So the key idea is that from the video, we want to disentangle and recover four factors that we can analyze. And the first is the camera trajectories, right? Imagine you are holding a camera and you are scanning the objects. So the camera is moving in a random trajectory around the objects. And then we want to recover the object geometry and also the segmentation information and the articulation dynamics. Since the four factors are entangled really closely to form the videos, so we need to disentangle these four factors clearly. And one insight is that we can, in this work, is that we can use pretty good motion priors to help us to analyze the 3D tracking points of the Gaussian points. And that can provide a pretty good, robust initializations for our optimizations. So the left side is a result that we use a 3D tracking algorithms to track the Gaussian point from a video input. And after that, we can filter the noise, and then we can estimate the articulation parameters. For example, the prismatic parameters or the revolute parameters according to the 3D tracks. And we can use this as a very good initialization method for the video input, and this will serve as a critical factors for improving the performance. So here is an entire pipeline of our models. So at the beginning, we have a sequence of video frames as the input, and we can use the VGT models to estimate accurate depths and also the camera pose according to the video input. This is an unposed videos. And we can use a pre-trained tracking models to get the 3D tracks from the videos. So basically for each frame, we'll have certain Gaussian points and we're tracking this kind of Gaussian point along with the videos. And after that, we can use the motion models to analyze the 3D motion priors, and we can use motion analysis models to disentangle like the static point and also the noise, the prismatic parameters, and the revolute parameters. And this kind of pre-processing and motion analysis can help us get a really good initializations of where is the centers and how the object can move and how many parts does the object have different kind of information we need for the reconstruction. And I think this is pretty robust since we can actually estimate the centers of this kind of this part and also estimate the prismatic and relevant parameters. And after that, we have initializations, and we want to estimate the deformation field that can apply to different Gaussian state, and we can render that into the final image to serve as the supervision for supervise the entire learning pipeline. So basically, we have input, we have initialized Gaussian and deformation field, and we use this as a supervision to render to different states, and we can compare the result of the rendered image and original image, and we can also compare the depth image with the original input. And this serves simultaneously as the supervision for the learning process. And actually, we get pretty impressive results from the video RGS. So basically, we get SOTA models on basically all the metrics. And notably, we can reduce the errors by about 2 orders of magnitude. For example, the ACES errors, the previous model has like 13 degrees, and we can have like 0.3 degrees. And this is a huge improvement compared with previous baseline models. And with evaluation analysis, we can find out that we ablate the motion prior and center initialization and also the deformation initializations. And an important message is that while reconstructing this kind of 3D assets, it's really, really critical to have a very good or perfect initialization models. So the entire joint optimization with Gaussian splatting and the video input, they can provide sufficient information for supervising such kind of optimization process, as long as you have good initializations of the part centers, of the clustering, and the assignments. And here are some qualitative comparisons with the baseline models. So we can have a clear clustering of the part centers and also the articulations. And we have done some experiments using the real-world data sets. So basically, the setup is that you can hold a iPhone and you can scanning the objects, and then you can interact with the objects using these articulations. And using that is all you need for our pipeline. And then we can jointly optimize the reconstruction, the camera geometry, and also the articulation parameters. And for example, here is a third view of how we can collect data and use this data as an input to reconstruct the microwave and interact with the microwave. And we can incorporate this into the simulation pipeline to simulate this interaction in the like ICLab or ICG. So after doing the reconstruction, we are still thinking about how can we scaling up the construction of this kind of 3D articulated assets without human labors. By video modeling, we are still need to put a camera to shoot the videos of articulated interactions. But can we use the generative model to scaling up the creation of these digital assets without any human labors? So we propose a work at this year's SIGGRAPH Asia called Dream Art. And the idea is that we want to use a single image as the input to generate an entire 3D articulated objects using the generative model, especially the generative video diffusion models. And the input is an RGB image and output is articulated objects, and it has articulated parts that can be interacted. So during time limit, I will go through this paper very quickly. So the overview of the dream art is composed by 3 stages. So in the first stage, the input is an RGB image, and we do the segmentation so we can have the part and also the base. And after that, we can do a mesh segmentation, and we can use the in-painting techniques to get the 3D mesh of this part and also the base. So then we can have the model input. So we can have a model input of the base and also the part. So this combined with the input image and the visible mask can serve as the input for the next stage. And then in the next stage, we want to extend the 4 parts of the input into a video basis. So we use a video model to generate different views of RGB image. And we can estimate the joints and texture from the synthesized view. So basically, we can estimate the joint parameters, we can estimate the texture parameters according to the generated different views of the RGB images. and we can refine the textures. So this is a pretty scalable pipeline for dealing with any arbitrary like object input, and then we can generate the 3D articulated assets according to the single RGB image. And then we can generate and we can scale up this to different RGB image from different categories. So basically, we have the input of the RGB image, and we do the segmentation, do the model completion, and then we synthesize different views of RGB image. We do the optimization of the texture and the joints. So that can produce us a very good textured articulated 3D objects. And after that, we can continually compose these 3D assets into a scene level by combining different object categories and with a background with certain lighting and like shadowing, this kind of conditions. We can use the like simulator to render these realistic 3D scenes based on the true art. Here are some comparisons. So after dealing with the object level reconstruction and also the generation, so our idea is that we can eventually build an agentic framework, which is published this year in Neuros. And we want the user to define what kind of the 3D things we need, and this is totally instructed by a natural language sentence. So basically, you can interact with the system. You can specify your instruction of what kind of things you want and how many chairs you want for certain categories. For example, designing a kitchen or designing a bedroom, a gym, different kinds of instructions. And we can combine the technique we introduced before. We can use the reconstructed 3D objects or the generated 3D objects to compose a real functional 3D scenes according to the input from the users. Right? We can have a very long sentence. We have different specifications for this room, the style, the number of objects, and how functional it should be according to your instructions. And also after the scene level reconstructions, the ultimate goal is to train a robot. So we can simulate this kind of rigid body or non-rigid body interactions according to the reconstruction models, and we can using the RL to really train the interaction models by pick and place and more complex interactions with articulated objects. So here are some takeaways from my today's talk. So today I'm majorly talk about how to advance the articulated object reconstruction and generations for robot learning. So basically, we think that scaling the assets of our articulated objects is very important, especially in a very efficient and cheap way. I think this is very good for our academic guys. And second, we found out that combining the Gaussian splatting and also the video modeling can be a really generalizable approach for us to collect the 3D articulation assets in lab setting. And this is really scalable. And for the approaches and for the models, we found out that initialization stage, including the center initializations and the clustering and the motion analysis from video, these are very, very critical according to the numbers it's critical for the reconstructions. And eventually we want to build up a scene level like scene synthesis so we can have a really functional space for the robot to do the interactions. And the robot can learn the 3D world and how to interact with this kind of 3D assets with rich interactions, rich categories, and rich textures. Yeah, I think that's the major part of my talk today, and thank you. You can take any questions.
Yes, thank you so much. I think we have time for one or two questions while we set up the chairs for the panel session, so just shoot that out.
Yeah, hey, thank you. Nice talk and nice results. I was curious, are you familiar with InfiniGen from Geodesics groups in Princeton? And they also have the simulation environment, right, like articulated objects. And I was curious how you compare your work with their work, just kind of to ask them compare.
That's a pretty good question. So the Infinity Gen actually they are done in Blender. So they have a lot of heuristic of how to combine and how to structure the object statistics, like the hierarchical and how can they combine together. So for the object level reconstruction, we think this kind of query is it's too much for the current object reconstruction. So we tend to reconstruct this kind of geometry and hierarchies from the object level. But for the scene level, we are still like using a similar way with the infinite gem. So we have certain constraint, maybe predefined or heuristics to define the relational between different objects to combine the object to a scene level 36. Yeah.
Yes, one more question and then. Oh, thank you for your awesome presentation. And I have a question of the generating more physically plausible assets. For example, for those assets to be manipulable by robots, I think we need for the object should be in metric scale.
Yeah.
And the parts also have some physical parameters like the inertia or the mass. So how are you going to generate impose those parameters to the generated assets?
I think it's a good question. So for the first word ArcGIS, we actually didn't consider that, but for the video ArcGIS, we leverage the current foundation model for us to like add on this kind of physical attributes. For example, for any object, we can like use the input video input, put it into ChatGPT, and it can help us to analyze how many parts we have and what is the category of the articulations, right? And then we can have like more requests like the inertial. So basically we can have average settings of the parts and inertial, this kind of physical parameters. And we can do certain randomization around this kind of average statistics. And then maybe we can use more labors efforts to have more specific requirements for the task. But nowadays we can use the foundation model to help us have very basic physical parameters.
Thank you.
Yeah, I think there's no questions. I think we have all questions. One more? Okay.
Sure. Why Gaussian plugin? Why don't you do box plugin? Like in your case, you would fit the whole thing with 3 boxes instead of 1,000 Gaussians.
So I think the ultimate goal is that we want to have a more flexibility, especially for the current one is for the articulated objects, and later on we'll have more like the soft body or different materials of objects. I think within Gaussian is a more flexible representation.
You can have multiple templates and have mixtures.
Yeah, I think that will also be a direction that we can try on. Yeah. Okay.
Yes, now it's time for the panel session, and while I manage my slides here, already the panelists can all come to the stage. Yes, now it works. I think the light is a little bit in your face, so we're gonna try to hide the projector in a second. Yes, for the digital participants, we have the Slido code again, so feel free to submit your questions over there. I'm not going to do a big introduction of our panelists since all of them already gave presentations today. Just to reiterate the names, we have Jeanette Hock from Stanford, Yunsu Lee from Columbia, Citron Hang from Big AI, I guess it's spelled, and Steve from Lightwheel. And our moderator, Alberto Longini from right now still in Naver Labs, but in a few days, KTH in Stockholm again.
Okay, thank you, Marcel, and thanks all the speaker for being here at this panel discussion. So I think that today we had 4 amazing talks that covered a wide range of possible solutions and way of moving forwards for manipulation of non-rigid objects. And I think that we had a very nice overview of pure learning-based methods from RGB and videos of humans, but also everything back to simulated solutions that rely on models of these objects. So my question is, what is the role of simulation now in progressing manipulation of non-rigid objects, And where does the real world data must take over to fill the gaps between simulated and real world modeling?
Okay. All right. So I have personally always been very skeptical of simulation, and in fact, in my lab, I think people are, except for sanity checking, first go to a real robot because it's so much easier for them to deal with a real robot than to deal with all the problems that show up in simulation, including like broken acids. I think we talked about that, right? And like getting realistic objects just in simulation. But of course also, actually I wasn't quite sure if you said everything's already there in terms of deformables or we still need work on that. I was a little confused by your talk. But from my perspective, and maybe I'm behind, I think simulating deformables is especially still not only very hard, computationally inefficient, and with a huge center-real gap, it's also, there are also all these assets missing that are clean. And I'm talking specifically not so much on articulated objects, although I think the assets there are also pretty bad so far, but deformables is especially problematic. But I think there is the potential to use simulation in good ways for manipulation, but I think the problems are again the huge center-real gap when it comes to deformables and computational speed as well of these simulations, in my experience. I'd love to be contradicted on this. And so that's where I think real-world data comes in. And so, yeah, I personally right now am very excited about using human videos, for example, that of course come with their own challenges and problems. But I think in terms of scale and realism, it has a lot of promise, but love to be contradicted.
Yeah, I think simulation's key role is to be data engines or evaluation engines. That's how I view simulation's role to be. For example, like today's talk, I've been talking about how we can use a simulation as a scalable evaluation engines, in which it is trying to solve some of the key bottlenecks faced by the current developments of robotic foundation model or even any robot policies. Because evaluation in the real environment is so noisy, so tedious, takes a very long time. And this is a key difference between scaling up robotic data versus scaling up language data. Because evaluating robotic performance in the real environments, I just don't see that is the most scalable way like going forward. And on the data side, I've been chatting with also folks at Google Robotics and Physical Intelligence. Like sometimes they have actually need to do some kind of budgeting. And by budgeting, what they mean is they want the performance of their policy to go from 80% to 99.99%. That's what's needed in the industry deployment. How much data do you need to collect? Where should you collect that data? Those are still all unanswered research questions. Without a proper evaluation, you just cannot answer those questions like in a more systematic way. If you don't know how to evaluate your model, you don't know how much value does your collect. So that I see are some of the key bottlenecks for the current robotic systems. In terms of the role of real data, I think the real data should come in really giving us this simulation engine that has strong correlations with the real world performance. So a lot of things like genetics wasn't convinced by simulation. It's because simulation doesn't give you the right thing to tell you if a policy works better in the simulation. Does the policy also necessarily work better in the real environment? That is what's currently missed by the current simulation engines. I think real data plays a very, very important role to address that specific like a gap. And no matter whether you use more physics, for the F equals ma, F equals mu mg, those most basic ones, you still need a little bit of real data to identify some parameters like friction coefficients for you to establish that alignment. But for more and more complicated scenarios like data, I would imagine them to play some more important roles.
Yeah, but maybe I also address Jeanette's question a little bit. So by the way, a huge fan of your research. Yeah, and so I would say, so I was being very clear. So I think for the rigid body, for the simulation, so I really see the problem is already solved. And you know, I think it's a good combination of not only R&D but also product solutions that we can fully solve that. for the deformables, for the non-rigid body, I still see that there is a lot of gaps. So those are the gaps that I mentioned in my last slide. Still, I think that right now we have all the great researchers working on the great solvers for certain deformables, for certain non-rigid body tasks there. So I really see that the algorithm is already there. It's more about how we plug everything into a better solution so that we can scalably and quality-wise to solve the simulation, the synthetic data problem. So that's basically why I'm asking everyone to contribute into this open source ecosystem in order to solve it. So that's the first thing. The second thing there is, so I really see that, so I'm a strong believer of data pyramid. So I don't see that simulation is the only solution. I definitely see it's gonna be a mix of everything. We are actually also investing in human data. Actually, recently we are collecting 1 million hours of human data, making egocentric for some of our top customers right now. So that's the scale I think the industry already is demanding from a human data perspective, right? But so I still see that for here, we definitely need a magnifier that can magnify a lot of data, but still I see that as the simulation. The first point from my part is I think there should be greater collaboration between academia and industry. For example, we collaborate with behavior team, we collaborate with RoboCasa, we collaborate with quite a few, I would say, the simulation-centric teams there. And the thing that I found out is it's very difficult for research for an academia lab to fully handle everything about simulation. It is not only about algorithm. It is not only about research. It is also about engineering system and also a lot of operations. Why try to solve everything fully automated? I really don't see the point of trying to solve everything automated. Does self-driving solve everything fully automated? No. So does AI get every data fully automatically generated? No. They actually leverage a lot of human collected data, right? Human labeled data. So we just need to have a very good, I would say, R&D and product combined solution in order to solve this. So I can see that all the major parts are already there. We have a lot of great talents, a lot of great research. We just need to plug everything together.
Yeah, thanks, Dave. And my personal view for this question is that the simulation may help us to solve like 70 or 80% of the problems, but the final like 10 or 20% is solved by the real experience or real robot, real data. And especially for the current stage, we are trying to scale up the object access, scaling up the training process, and a lot of things cannot be done like in a very efficient and like cheap way or like economic way in the real world. And you also mentioned that in academia setting we don't have a lot of budget to do this kind of trials. So currently, I think we can like put the part like the real to sim this kind of reconstruction and also the RL training into the simulations. And for like the locomotions and for some motion priors, the robot can learn how to walk, how to move, and how to interact with the rough trajectory learning from the simulator. And for the tedious one, the physics interactions and the tutorial that Jeanette has mentioned, I'm a believer of the real data. So we eventually need the real data to solve the long tail distributions and especially for the like interactions, this kind of physics. So combining the best advantage of the simulator and real world data and how to smartly combine this kind of two data is a question for the current our current researchers. And I think the strategy is plays an very critical roles in how we can like develop the models. Yeah.
Okay, thank you. I think this was interesting, and it seems to me that there's sort of a pattern, maybe some different opinions on what's the role of simulation, but in general, real world data is indeed needed. Which brings me to the next question, that is, especially working in the real world, it's hard to access, for example, the state of the object because we have different ways of perceiving the object, different sensing that sometimes depends also on the task. So how do we use this data to create representation, or better, should we work towards a general representation for non-rigid deformable objects, or maybe we should more look into task-specific representation, also tailored for the sensing that we have available?
I can go first this time. And so we have been using a lot of techniques in computer vision to really pursue a good representation for robots. And I'm a believer of the general representations, and I think along with the time, the people are developing a lot of good techniques for modeling the objects. For example, currently we have the VGT for a better like pose estimation and also for reconstruction. We have Gaussian mapping for an efficient and flexible presentations. And I think these techniques are really changing the views of how we can tackling the robotics problems. And from our experience, we think that the development of the computer vision techniques can really help us to develop a general representation. So we don't need to add a lot of ad hoc information or hierarchies, private information for this model because the more prior you are adding on to the models, the model can really hurt the performance for the generalizations. So I think a general representations might be a good goal and will be the eventual solutions for vision and for robotics. Thanks.
Actually, I would like to argue that there may not exist one general representations like that works deliver for all tasks. So even if you think about human interacting with different objects, interacting with rigid versus deformable, you are actually really thinking about them differently. You have some kind of rigidness priors to constrain the motion of that object. We human actually do that when we're thinking about the evolutions of a specific rigid object. Meaning, depending on different object type, the representation might need to be different. And given the same object, but depending on different tasks, if your task is just to grasp the objects, you only have to know the general shape of that object. But if you want to open the cap of this water bottle, you have to have fine-grained descriptions about different semantic parts of the same objects. Meaning, depending on different tasks, even the same object might afford different type of representations. Another example is within the same task, but different task stages. If there's an object that's far away from you, you only have to know there's an object out there. But you're getting closer and closer to that object. You start to focus on more local geometry and details of that object. That meaning even if in the same task, but depending on different stages of the same task, the representation might also need to be different to get the best trade-off between the efficiency and effectiveness of doing the task. So yes, there has been a lot of vision foundation model that can give us those kind of intermediate representations. Triaging with robotics is actually benefited hugely from the developments of vision foundation models, 3D reconstruction, key points detection, tracking, etc. But if you're really looking at many of the models that all really work out there, they actually make different selections, make their choices of the representations. Jeanette also mentioned in her talk that for many of the different kind of works, we're actually selecting different types of representations. So I actually see going forward, even if there exists one very, very general representations that sort of works like across the board, but if you really want the performance to go to the extreme level, some specializations on the representation might need to be necessary.
Yeah, I think I understand what you said, right? Like you want a general representation. I understand that goal. That's of course, would be cool, but I'm also skeptical if that's achievable. So I agree with you as well. And I just want to define representation a little bit as well. So you can think of a representation for a simulation in particular, right? So if you want to have articulated object, you actually do choose a very specific representation of these articulated objects so that they are simulatable. Or if you can use for kind of things like DOE or this flesh animal that you had, or rope or whatever, you might use a particle-based representation, or you would use a mesh or something. And these are all representations that are about representing an object in 3D in simulation, right? Like so that you can actually physically simulate it. And the other side of representation is whenever you feed as input to a policy. And that might also be a mesh or articles or, this articulated object with its revolute and prismatic joints and all of this. But it could also be an image or a point cloud, segmented or not. And so, yeah, so these are the two different sides of representation. And again, I'm skeptical for either side that we will have a general representation. Again, I understand that we would want that, especially on the input side. But maybe, for an industrial task, it might actually make sense to have a very specialized representation because it gives you more accuracy. So, let's say you do electronics assembly, right? Like, so you have to deal with cables, but you also have to do with the rigid objects, right? So in order to do really well at it and to be really fast and you're in a particular class of task, maybe you want to have actually a specialized representation so that you can deal with this kind of task rather than being general. If you had a general one, maybe that gives you advantages in terms of switching between different tasks faster than if you had like a specialized representation. But that it's like a trade-off there. So honestly, I don't have an answer. I'm skeptical of the general. I understand the wish for having a general one, but I'm skeptical if it will ever happen.
Yeah, I would say just from an industry practical standpoint, so currently we are not doing it as a generalized way, but potentially as a specialized way. For example, some of the customers, they want to have more specifically tactile sensor related simulation, right? Then we need to have much more fine-grained simulated access there. Some of the customers, they are more like in the computer vision. Some of the customers, they want to have large-scale data collection. Some of the customers, they want to be able to run large-scale RL. And for example, if you run large-scale RL, you actually have to do certain optimization to make it highly efficient. So all of things could be a little bit different. Yeah.
Great, thank you for sharing your opinion. So in the interest of time, I would like to close with a question from you. I would like a very concise and answer, which is from an outsider. Let's assume that you know nothing about robotics. All these demos that we see circulating online seems like the deformable and non-rigid object manipulation is close to be solved, which I disagree. So I would like to know, in your opinion, and again, short answer, if you had to pick, what's the biggest hidden challenge behind this video? So we see progress, but actually there are many challenges. And what would you pick to share in terms of what's really still unsolved, an interesting open problem?
I think I have been talking about it in my talk. Basically, building a world model, either using physics or learning, or some mix of which, and has very, very strong correlation with the real environment for all different kinds of deformable objects. I think that's, to me, is some of the challenges I really want to resolve.
Yeah, maybe I would say I agree with you. So we don't actually know what even as like non-naive people, even as roboticists, I don't think we know what the real challenges are because all these social media videos and the videos from academic labs, including my own, are doing like pretty low scale evaluation, right? Like just because we sometimes have to in a very particular task. And so because of that difficulty of evaluating in robotics, I don't think we know what the biggest challenges are and what the way forward is. And before we have them figured out, I don't think we can even explain necessarily convincingly to non-roboticists what the biggest challenges are. Oh yeah, hardware, robot hardware is really bad. I don't know if you noticed, but it's pretty bad compared to mine.
Yeah. So I would just say that how to scalably and production-wise to produce high quality data either through simulation or through other methods that can really support, accelerate the whole embodied AI foundation model building. That is the most important thing that puzzles me and also that challenges me to work on this every day.
Yeah, for me, I really support the idea of a better evaluation and also a stable hardware. So we have the support for the fair evaluation across labs. And for me, personally, I really want that we can have a better like tactile mode for the interaction, especially for narrative interactions, because current position control, a lot of the current control methods, I don't believe in the end it can produce a very good narrative interactions that doesn't hurt the objects and also have very accurate manipulation accuracies. So I think we need to have more like accurate tactile simulation or tactile hardware, so we can really do a better control that is underlying this kind of robotic task. We can have impedance control with the force and also the position. I think only if we have these kind of requirements for the robots, for the hardware and software, we can believe that the demos and evaluation can be reproduced across lab and across different places. Thank you.
Thank you once more. Let's give a round of applause to our
Presence.
Yeah, we as our organizer wanted to thank himself partly from Sweden. Well, no, it's just
It's for us, thank you.
Then thank you again.
Thank you. All right. Thank you. Thanks again to speakers. And before the workshop, I saw the thing flag and thought, make sure to not give that to Janet. Yes, there's not a lot to do. Just some closing formalities. We have a few awards to give out, sponsored by Lightwing. First, the extended Attribute Award. We have two finalists, Mesh, Spread, and Slice, and Learning Equivalent Neural Content Object Dynamics from Few Interactions. And to keep it short, leave you out for lunch. The first winner is Learning a Coherent Neural Object. Let's please come on stage. Steve, you can also come up. Since you're the sponsor for this, maybe here. Oh, where's the on there? Yes. On stage. Okay, great. Can I take a quick picture? Oh, cool, sure. Congratulations. Thank you very much.
And run the.
Okay, perfect. Then also for the best poster, because we always like if people spend time on actually visualizing their contributions. I'm not sure if any of the authors is still here or if they disappeared for lunch. Otherwise, we're going to reach out to them. The best poster goes to Mesh, Spread, and Slice. Already lunch, so we will find them later and give them this effort. Yes, the last thing to do is we're going to organize a dinner later in the evening. So if you have nothing planned yet, feel free to sign up. Just a few organizers of the workshop and attendees are going to come together and have some drinks and food. So just feel free to join us and continue what has been going on here. Otherwise, it's been a great pleasure to have so many of you here and keep the discussions going all over the workshop and have a good time. So